Hi, good morning once again. Good morning, everyone. Hello, am I audible?
Yeah, good morning, sir.
Good morning, sir.
Yeah. So today first we'll discuss about uh, structure of the B tree and the B plus tree. We will see the insertion of B tree and the B plus tree. Then we will see hashing part, uh, bitmap index, then hashing part, dynamic hashing. Then after that we'll take your doubt. So let me share my screen. So my screen is visible, right?
Yes, sir.
Okay. So what is B tree? B tree is a simply balanced binary search tree, right? And the structure of the B tree is like that. This is the block pointer. This is the block pointers, and this is the key, and the corresponding is the record pointer. And this is the like PB2 is the block pointer, and the corresponding key is the key and the record pointer. So yeah, someone okay. I'm sharing the link. So so if P order B tree means P order B tree means maximum number of child pointers, or it can also refer as block pointer, sometimes child pointer or block pointer per node equal to P, and the maximum numbers of key equal to n minus P minus 1, right? So if it is P order B tree means per key can accommodate maximum numbers of block pointer is P, and the maximum numbers of key can be accommodated per key P minus 1. Hello? Yeah. So if it is 3 order bit tree means maximum can be per key can accommodate 3 child pointers and 2 key per node. So up to that everyone got it?
Yeah,
Uh, that is maximum. What about minimum? Minimum will be one, right? In all of them.
Yeah, minimum will be the maximum numbers of key will be the n minus 1 by 2, where n is the order of what is the order of bit, right? So if it's 3 order, so minimum will be the 3 minus 1 by 2, so it will be 3 minus 1 by 2 equal to, right, 1, right? So it will be 1 key per node, and block pointers will be the n by 2. So numbers of block pointer minimum n by 2. That will be 3 by 2 equal to 2 block per node, 2 block pointers.
So when you're saying n is basically the same p,
Yeah,
right?
P, or you can P minus 1 by 2, you can say.
And
If you are n is the order of bit tree, you can simply
okay, and n by two is the minimum number of
block pointer or child pointer.
child pointers.
Yeah. So up to that everyone got this? Okay.
Yeah, sir. Yeah.
Yeah. So
in databases, what is the typical pre-order? Is it like third order or
yes, so if it is three is, database is not necessary 3 order or pre-orders. It's not. It can be, you can use any order.
got it?
And in case it is, I mean, n minus 1 by 2 is a fraction, then what do we do? I mean,
So,
like in n
so we
minus,
have given ceiling
supposing
value,
n is
right?
even,
n,
right?
n minus 1 by 2. Suppose is 4. If it is 4 order bit tree, so 4 minus 1 by 2, we get ceiling value. So 3 by 2, 1.5. So we will get 2. Ceiling
Okay,
value.
we round it up, is it?
Yeah, it is ceiling value. Okay. So once again, I am explaining.
It's always the next higher number because it always ends at 0.5. No?
Yeah, yeah. So this is the uh, structure of the bit tree is basically like this. This is the block pointer, and this is the key, and the corresponding it's record pointer. So what the record pointer means, what the actually data is present. So it will give the address of the that location where data is present. So this is record pointer. It will give the where actually data is present. It will give the address of that location where the data is present. So everyone, what is record pointer, what is keys, and the what is block pointer?
Explain one, sir.
Yeah, child pointers means it will give the address of the child, your left subtree or the right subtree, right? So it will give the that address, right? It will link, right? Where the key is the actual key, right? What like 20, 50, what the actual key, and the record pointer, it will give the where the actual data is present. It will give the address of the that location, right? So this is the block pointer, and this is the key, and this is the record pointer, right? Record pointer. Then after that, this is the block pointer or child pointer, this key, and the record pointer, and this is the block pointer.
So if you can take an example of a database, let's say a relation has maybe like maybe four attributes,
Yeah,
and then first two are, let's say, the keys. It's a concatenate, like two fields. Uh, First column, first attribute A1 and A2 are the primary keys, and
yeah,
then A3 and A4 are like non-prime attributes.
yeah.
Then how, I mean, it is stored, then I think it will be very, very clear.
So it will generally store in the key attributes, right?
Yeah.
So uh, yeah, I think I'm not sure, but I think my there is A1 and the A2 is the key, right?
Yes, sir.
So it will like store, suppose this is the first name, or this is the last name, right?
Yeah.
So I think that will state combine of both, right? So this is
Yes.
the one, this is the like first name is the A, this is the B. So it will keep corresponding to the combine of the both. So I'm not sure. I'll get back to you in the next session.
Okay.
Yeah. So how it stores. Okay.
Sir,
Then
record pointer, what it will record actually?
so where the actual data is present. So in the disk somewhere is the present, right? Or the data, or the suppose there is a one tuple, right? Suppose this is the roll number, and the first name is the student is sum, and the like address, right? So like address. So it this tuple is stored in the someone in the disk, right? In the disk, or the hard disk or the SSD, someone in the somewhere store this tuple. So it will give the where address where the actual data is present. So it will give the address of the data where the actual is data is present. It will give that address. So you got it?
Yeah, physical address.
Yeah, physical
Got it.
address.
What about the key? Key is the primary key then?
Yeah, yes. What will be the?
Key is the primary key, sir, then?
Yeah. Key is the generally is story. The key is the primary key where we take the primary key.
So I have one question.
Yeah,
So we have said, supposing it is a 10 order B tree,
yeah,
right?
yeah,
But I have only say five keys right now.
yeah.
So then I can't use my B tree, right? Because it has to be the minimum keys that can be used
So
are 10 minus 1 by 2. I mean,
So,
supposing I have 2 or 3 keys only, right?
so accept the root node. I actually accept the root node. I'm forget to telling. Accept the root node. This is the minimum.
Oh, so minimum is only, it is not for the root node,
Yeah. So,
right?
yeah.
Yeah, that's what I had my doubt when you said that.
Okay.
Because root node can be only one key can be there, right?
Yeah. Accept the root node. Okay. So this B tree structure is everyone clear? Okay.
Yes.
We will see the insertion, right? Okay. So construct a three order bit tree from the keys inserted sequentially. So three order bit tree means
Two keys can be there.
yeah, maximum child
Two
pointer
keys.
equal to 3 or maximum numbers of key will be 3 minus 1
2.
equal to 2, right? Okay. So we'll insert in the empty binary tree. So B tree. So let's insert 20, right? 20, and this will give the record pointer, right?
So can you connect these details to the picture what you are already explaining? Like three order tree, yeah, there is no need for further explanation. Max child is 3. Can you go back to the picture and just point out what we are telling? Max 3.
If not, explain in an Excel sheet, sir. Excel sheet is.
Yeah. So
No,
which part?
what I am requesting is just how do we connect this picture to all these attributes what we are talking?
Okay, we'll see with the when we insert, we'll see how uh, you connect
Oh,
in the
okay.
picture. So I'll show. Don't worry.
Okay.
Yeah. So yeah. So let's insert 20, and this will give the record pointer corresponding to the record pointer, right? And this is the block pointer. So initially, if there is no block pointer, this will initially null, right? It will be null, and this will be null. Then after the inserting of 50, right? If you insert into 50, like it will a maximum key can be stored 3 order bit right 2, so it can be keys are no available, so it will insert 50 and corresponding it will give the record pointer, right? So up
Sir,
to
it
that,
is 2. Sorry to interrupt, sir. Sir,
yeah,
it is 2 because 3 minus 1 equal to 2, right?
maximum can be 2.
Okay.
So if it is 3 order bit tree means maximum child pointer or block pointer, child pointer sometimes also referred as block pointer equal to and or whatever the given 3 order, right? So it will give 3, and maximum key will be n minus 1, so it will be 3 minus 1, so it will be 2. So maximum each node maximum accommodate 2 keys, right? So 1 keys and the 2 keys. So up to that is clear. Hello.
Yes, sir. Yeah.
So now we'll insert 40. So if you insert 40, you can see that each node can accommodate 2 keys. So this is overflow bracket, right? Hello. So what we'll do is middle elements, right? So we will sorry. So this 40, when we insert 40, so in the middle 40 will insert, right? Because 20 40 is greater than 20 and the less than of 50, but you can see that each node can accommodate only 2 node, so it will be right, so it will be split in the middle side. So what I will like that 40, then 20, and the 50. So up to that is clear. So it will be like that.
But actually, we required minimum 2 keys in each block. No?
Minimum 2.
Actually, there is a 3 ordered thing. So 40, and there will be a space in that.
So if it is 3 order, minimum keys will be n minus 1 by 2. This is the ceiling value. So what is n equal to 3? 3 minus 1 by 2. So 1, right? So minimum keys can be 1, right?
Okay, minimum
Yeah.
keys will be 1,
Yeah.
but 1 will be empty.
I did not get 1 will be empty means. You
A
can see
3
that.
order B tree, every block having two keys.
Yeah.
Minimum there should be 1 key, and
Minimum 1 key,
Maximum
maximum
two keys.
2 key, maximum block pointer or child pointer
3.
3.
3, and 3 child pointer block BP, and minimum block pointer 3 by 2 equal to 2. A ceiling value of 3 by 2. So ceiling like that 3 by 2. So it 2 minimum 2 block pointers, right? Yeah. We can accommodate also, like when other key will be inserted, it can be inserted in that place, also in that place it can be, but minimum will be the 1 key. So is your doubt clear? Hello?
yeah, sir, go ahead, sir. I
Yeah.
will after completion.
Okay. So up to that is clear.
Yep.
Okay. Now up to that is down. Now when we will insert 80, right? So 80 is right greater than 40, it will go to the right subtree, and it is greater than 50. So 80 will stood like that
50
place.
from IT. Yeah.
Yeah, right side of 50. So when we insert 80, so it will be like that. Okay. Now while we insert 90, right?
Yeah.
So it is greater than 40, it will go right subtree. It is greater than 50, it is greater than 80, and it is, so 90 will be in that place. But you can already see minimum maximum key can be 2, right? So it will split, so split in the middle, right? So split in the
Yeah.
middle.
80 will go up. Yeah.
Yeah, so it will be 40, then 80, and like,
Hey, good morning, Karthi.
yeah.
Hey, and VMC-ல வந்து அந்த பிரேக்
Please
மாத்துவாங்க
mute
இல்லையா?
yourself.
அதை கொஞ்சம் வீடியோ எடுக்கணும்.
Pradeep, can you mute?
சரியா? நீ என்ன ஆனந்த் கொஞ்சம் ஃப்ரீயா தான் இருப்பான். ஆனந்த் ஆனந்த் ஃபோன் பண்ணி சொல்றியா? ஆனந்த் நார்மலா ஃபோனே எடுக்க மாட்டானாமா.
Thank you.
Yeah. So it is right side up, it will be get 20, right? And you can see that 50 is greater than 40 and less than 80, so it will be like that, and 90 will be greater than, so look like that. So up to that is clear after instances of 90.
Yes.
Okay.
No, sir, please go one step ahead. One step. Yeah.
Okay. So okay, let me erase. After that will, so when we will insert 90, right? So 90 is greater than 40, greater than 50, and greater than 80. So 90 it will be here, but it is 3 order bit tree, so maximum can be 2 key. So it is overplay of bucket. So 80 will split, right? So 50, 80, 90. So middle element will be split, right? So 80 will go up. So when 80 will go up, 40 and the 80, so 20 is less than 40 and
So
50 is,
here 80 is going to 40 because the node containing 40 has one place available.
yeah,
Because
yeah, on plus available.
otherwise, we would have actually kept 40 at second level and then put
Yeah,
50 and 90 below it, right?
yeah. So we'll
That's
see that also.
So
That
why can't we take 50 up similarly? Why only 80?
no, middle element,
it's a middle element,
middle.
middle element. So uh, you can see the 90 will be like that. So middle element is 80. So 50 will go up.
Okay,
Right?
it's always the middle element, sir, which goes up?
Yeah, it is always middle element.
Okay.
If it is even, like if it is 4 order tree, so 10, 20, 30, 40. So middle element can be 20 or 30, right? So you can split 20 or 30. But if you split 20, so the whenever next element will be inside when the bucket pro over, so if you split that place, you have to split that place, right? So every time you have to split that place, you follow one order. And
Okay. Okay, sir.
if you split that place, so in the next time also you have to split that place if it is even order.
Okay, sir. Got it,
If it
sir.
is odd,
Thank you.
like if it is odd, you can split middle, right?
Yeah, odd is good because
Yeah.
there's no tie for the middle position. I think
So
the even order.
generally B tree is odd order generally.
Yeah, yeah, that's good.
Yeah.
Too much of confusion.
Yeah. So 50 is uh, greater than 40, right? And the 90 will be is greater than 90. So like will be that 40, then the record pointers 80 record pointer. This is the child pointer. 20 record pointer, 50 record pointer, 90 the record pointer. So up to that is clear. Okay.
Yes, sir.
Now we'll insert 10. So 10 is less than 40 and then less than 20. 10 will be inserted in that place. And it will be like that.
Yep.
Yeah. Next is insert 30, right? So when you insert 30, it is less than 40, greater than 10, greater than 20. Insert will be like that. We can see that 10, 20, 30. Node is already full. So it will go up, right? 20 will go up. When 20 will go up, you can see that this node also present maximum numbers of keys, right? So what will happen? You can 20, 40 and 80. So this node also will split in the middle element. So 40 will go up, right? So like that.
Interesting. Yeah. So
40,
instead of splitting down, it's kind of pushing up.
yeah, 40. Then it will give 20, then 80, then 10, then 30, then in this place 50 and the 90. So this one will insert, and everyone clear how will split everyone, or shall I explain once again?
I think we
No,
do.
sir, it's clear, sir.
Okay.
It's more
So
as of a recursive thing, right, sir? I mean,
yeah,
you keep going up.
yeah, going up. Yeah. So it will be like that. Okay. So up to 10 is clear. So when we insert 70, it is greater than 40, it is less than 80, and greater than 50. So it will be inserted like in this place, right? So we can see that
That
7.
means it's basically self-balancing. Every time we're
Yeah,
inserting a new element, it's bubbling up and it's self-balancing, right?
yeah,
That's
yeah,
very nice.
yeah.
Yeah. So is it like a hip? Because I think we are reading somewhere like a hip. It's a special. It looks like that, right?
I did not know about so much detail about hip, so I did not comment about.
Okay. All right. So no problem.
Yeah. So yeah, 70. So when we insert 60, so it is greater than 40 and the less than 80 but greater than 50, so insert in this position, right? But it's this node is already full, so 60 will go up, so like that 40, then in that position 60, 80, like that 50, and the 70, and the like 90, so like that. So insertion of bit is clear for everyone.
Yeah.
Okay.
So a question on this. So now we have 1, 2, 3, 4, 5, 6, 7, 8, 9 values, right?
Yeah, yeah.
So if we have to find out max, what is the maximum hops required to search a value? Do we just take, because it is 3 order,
Yeah,
so 3 to the power, I mean, we have to take the log of 9 to base 3,
yeah. Generally, we take and the best case log 3 9, whatever
log
the
3 9 is the
yeah
best
best
case,
case.
right?
Yeah, yeah, best case.
When log 3 9 is 3 to 3
Two.
square,
Two.
right?
Yeah.
Uh,
So
uh,
that means 2 hops.
yeah, yeah. So two up. So it is best case. In the best case for searching, in the best case log 3 9. It is because 3 order between.
Okay. So whichever is the order, we take the log of
Yeah, yeah,
base of that, right?
yeah, 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 yeah. Okay. So after that is
And,
yeah,
I just want a clarification.
yeah,
I mean, without getting into the details,
yeah.
how do we end up with only one node on S20?
Uh,
But 20 has only two nodes, 10, 30, whereas we have 60 and 80 as a two node,
yeah,
and that has a child node of 3.
yeah, yeah.
Can you explain based on the basics what you are trying
So
to?
so that minimum is only for leaf nodes. It's not even for internal nodes then, right?
Minimum is for leaf nodes, and
Correct?
the
Minimum.
minimum is 2.
See, if it is ordered 3, the maximum block pointer is 3 and the minimum block pointer
Is 2.
is 3 by 2. It is
Oh,
2, right?
1. Yeah,
Yeah.
2 and yeah,
So
1.5
this
2.
will point to null, right? This will point to null. It is
So
present block pointer.
that makes all the child to have 3 blocks,
Yeah,
right?
yeah, this yeah. So you can see that there is present two block pointers, but all the leaf uh, whatever the in bit is will point to the null. Block pointers will point to the null,
Hmm.
right?
So can I call the last row as a child node?
A loss, yeah, yeah,
Last row as a child node.
yeah. This is the
Leaf node.
leaf
Leaf node.
node,
Leaf node, yeah,
yeah,
okay.
leaf node.
But
This is
somewhere in the previous slide you are referring to as a child node. What is that
the
then?
yeah. Child pointer means you can also call child pointer or block pointer. This is the child pointer
Ah, okay.
or block pointer. It can refer as both child pointer, sometimes called as child pointers, or block pointer. Both is right.
All right, okay. So
So
that's equally true for 20, 60, and 80.
yeah, yeah,
Can
20.
be called as a child
Yeah,
pointer.
this is block pointer or child pointer. This is block pointer or child pointer. This also 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 block pointer or child pointer, and
Okay,
corresponding
between
like
60 and 80,
yeah.
you have a common point block,
This
no?
yeah, this
That
is
belongs to where?
Hello, hello. Am I audible? Hello.
yeah, yeah,
Yes, sir.
Okay. So you can understand it's like the 40 is the grandfather,
Ah,
right?
yeah.
And this is the parents and this is the child. But 20 is parent, but he is also the child of grandfather, right?
Okay.
Okay, so 20 is also child, 60 and 80 is also child, and 50, uh, this 50, the pointer pointed to the 50, and 70 and 90, these are also child pointer. Means this pointer above here from coming from 60, so it is child pointer.
60
And
and 80 put together is a single block or two blocks?
so in single block,
It is a single node.
yeah, block or node same, we every node allocated one block, so you can think in the memory
Every
tab.
node reflected one block,
Yeah,
and the minimum maximum pointers are defined in the formula,
yes,
and 2 and 3. But now here we are having a block within block, having 2, 3, 4, 5 blocks.
So this
How
key,
to read this one?
so this is contiguous, right? So the block is like the memory locations are continuous. So that's why once we reach 60, we can reach 80. I guess,
yes, yes.
right?
No. What I am just really not able to connect to the minimum, maximum, and block sizes. And when it's a super block containing 60 and 80, which we have not talked in theory part,
See,
and the number of blocks in that one is 5 blocks. It's neither 2 or not 3
see. Let me
individually. So
answer.
it's a
If it
5
is,
blocks coming in. How do we really
see,
understand that?
say, let's say once. If it is three order tree, right? If it is three order tree, maximum we read maximum block pointer is 3, right? The
3. Yeah.
and the maximum key will be p 3 minus 1, it will be 2,
2
and the minimum key it will
is
be
1.
n minus 1 by 2, and we will give the ceiling value. So 3 minus 1 by 2. So you can see that per block or per node, it is minimum key is 1, so it can be 1, and
Oh.
maximum key you can see that in the here maximum can be 60 or 80, maximum can be
Okay.
2.
Oh, that's how we should read that block,
Yeah,
is it?
yeah.
Okay.
Yeah, so if it is overflow, then we have to split. So like previous we have split. If it is overflow, maximum can be 2. If it is 3, then we have to split. Like when we insert, we have seen how to split. We have to split in the middle element.
So we have always a null blocks on either side, is it? That's just to justify the maximum, is it?
Max
The null blocks are there on either side, both the sides of the
Justify minimum to
justify the minimum, is it? No, justify the maximum.
minimum.
So
Minimum?
see that in the leaf node, you can see that the 10 is present, right? But
Mhm.
this is
Yes.
not any child pointer block pointer, so it is referred to the null, right?
Okay.
You can this child pointer or block pointer referred to the null.
Okay.
It is present,
Okay.
but it is referred to the null.
Okay.
So up to that is clear. B tree,
Yeah. That's up to that
Also, sir,
point.
when you say B tree, is it the binary tree that we refer
B
to?
tree is a balanced binary tree.
Balanced.
Balanced binary. But
Yeah,
sir, whenever I think of binary tree, I think of a node and then two children.
yeah.
So like here in the last leaf
It is.
node, we have 50, 70, 90, which are three children.
You can say
So
that MOA balanced binary tree.
which one's a
MOA balanced binary tree.
MOA?
MOA balanced binary
Okay,
tree.
MWay. Okay.
Yeah.
And what does that mean, sir? MWay?
It means with three order means it can be 3 OA, right? So it can be.
Oh, okay, sir.
Okay. So up to that is clear. We'll solve one numerical then.
One last question on this.
Yeah. Yeah.
See, generally, when we're talking about this, we are interested in.
Yeah.
So, in this case, any search we need at the maximum number of nodes to search any value would be 3 here, right? First
Ah,
level, second level, and third level, right?
yes. Maximum can be 3.
Height of the tree, basically.
Yeah,
So in
basically
this
height of
case,
the tree. Yeah.
log of n. N is the number of elements, and
Mhm.
base will be
It
the
is the
order of
best
the.
case.
Oh yeah,
Max,
base
yeah,
case. Yeah.
yeah, best case.
best case and worst case. Is there any worst case also?
Worst
Log
case,
2.
I did not know. I will tell about the next lesson. What is the worst case?
Okay.
So it should be log 2, right? Because like you have minimum block size, maximum block size is 3. If you take the minimum, then it will be 2.
Uh,
So it should be log 2 9.
yeah, I will confirm about the next
Okay, sir.
session.
Okay.
Okay. So now please try to solve. I will
Sir,
give.
and last one more question, sir. This is actually block pointer, no?
Yeah, yeah.
In left side, if first 20, if we see that address is kept in that small blue dot.
It is the record pointer.
Yeah, record pointer.
Yeah.
So 40's block pointer is its child pointer. Actually, it is mapping to that particular dot, right?
No, no. Record pointer or child pointer is different. This is the child pointer where it is referred to the left subtree, right? It will link to the left subtree, and this block pointer is linked to the right subtree. Whereas
In block pointer, what it will be there? There it will be address of 20, right?
no, no, it will be what the this left subtree, right? Left subtree. It will have address of the left subtree. But where in the this will store the right subtree, right? What are the this node is present, right? Address of the this node and this node where actually this node is present, or it will give the record pointer where actually 40 is present.
Right, sir. Thank you.
Yeah. Okay.
So these block pointers, they're stored in the random access memory or storage, because record pointers are stored in the hard disk.
Yeah, yeah.
But these block pointers and child pointers, are they addresses in the RAM memory, or is it permanent storage like hard disk?
uh, this is the data structure, so I think some after the insertion some are stored in the
Yeah,
in,
yeah, because if it is in memory, it will be very, very fast.
yeah, it will be very very fast. Yeah.
So that's okay, fine, no problem. I think understood.
Yeah. So this is the consider a bit tree with the following properties. Block size is given, per block size is given 1024 per block size, and the key size is 16 bytes, and the record pointer size is 8 bytes, and the block pointer size is 8 bytes. So find out the maximum order possible for the bit tree from the given information. And this is the block size. So you can see that this is the block size, one block size, right? So you have to find the maximum order possible for the bit tree.
Right. बताइए.
Yes.
Mm-hmm.
Pradeep, can you mute?
Yeah, yeah.
Yeah.
Okay, you can continue.
Yeah. So uh, so we have seen also in the so let's draw the structure of the bit tree. So this is the block pointer or child pointer, and this is the key and corresponding to the record pointer. Then this is the block pointer, then the key, and this is the record pointer, RP, like that. This is the block pointer, sorry, the key and the record pointer like that, and this is the block pointer, right? So if it is p order tree, so maximum can be maximum block pointer.
So this is a four order tree, right, sir? Which
No,
you have
no,
provided?
no. This is we have asked maximum order possible with the given information. What will be the maximum order possible? So
Okay,
maximum
sir.
block pointer is p, right? And the maximum key can be p minus 1, and the maximum record pointer will be p minus 1. This is right. After this is clear. Hello.
Yeah.
So you can say that what about the block pointer, size of block pointer, right? So size of block pointer is
8
8
bytes. Yeah.
8 into p plus p minus 1 is the record pointer, right? So p minus 1, the record pointer size is 8 bytes. 8 plus p minus 1 is the maximum key, and key size is 16, is less than equal to 1024. This equation is clear up to that. If you did not understand, I will repeat once again. Don't worry.
So we are assuming that it's a p order B tree.
Yeah,
So with that, maximum block pointer will be p. The maximum number of key is p minus 1. That's understood. And then maximum record pointer will be p minus 1. Yeah,
yes,
corresponding to each key. Yeah.
yeah, and it is,
And
we have given block size is 1024, so it will be
yeah, that's the upper limit of everything taken together has to be less than 1024.
1124.
Yeah, so since the block pointer is 8, so this is 8p. 8 times p gives us the space required to store p block pointers,
Yeah, yeah, block pointer.
right? If we have got p minus 1 keys, then each key size is 16. So it should be p minus 1 into, oh, 8. I don't understand. What is that p minus 1 into
Uh,
8?
8 is record pointer, right?
Oh, record pointer. Yeah. Okay. So
And
that's
the
the one.
record pointer we have given p minus 1 into
Right,
16.
right, right. Yeah. And then we keep the key sizes. So that is p minus 1 into 16.
Yeah, yeah.
Is it right to say that maximum key and the record pointers are always equal?
Maximum key, yeah. So, yeah, it will be always equal because key and the corresponding record pointer, right? So it will be always equal. So because
So,
you have given, see, this is the key and the corresponding record pointer. So if it is the key present, it will give the corresponding record pointer, right?
yeah, okay.
So record pointer means what the, it will give the address of the that location where the actual data is present in the physical memory, like hard disk
Oh,
or
okay. Please go back to the problem. Is the redundant data is there, and if so,
yeah,
the record pointer size and block pointer size
yeah,
both are necessary to solve the problem?
yeah. Both are necessary. Both are, because see, uh, this is block pointer, the key and the record pointer, right? So in the, if it's p order B tree, so maximum block pointer will be the p, and the maximum key will be the p minus 1, and maximum record pointer will be the p minus 1.
No. Just going back to my question one, block pointer and the record pointer always equal. Keys
Yeah,
are
always.
always equal.
Yeah.
Then, if is it not redundant to have both together?
See, it block pointer, see, key and the block pointer size may be different.
Key and the block pointer size may be different.
Yeah,
Okay.
size. I'm talking about this. I'm talking about the size. It both are equally, means whatever the numbers of key and the numbers of record pointer will be the equal, but size may be different. Size of key and the size of block, size of key and the size of record pointers may be different, but the numbers of key equal to the numbers of record pointer.
Oh, confusing now.
Yeah, see, numbers of, sorry, number of key equal to numbers. I'm talking about the numbers.
Count.
Yeah, count numbers
Yeah.
of record pointer equal to numbers of key equal to numbers of record pointer, but the
Okay.
size of that key and the size of that record pointer may be different, and it will be
And the
different.
size of the key is represented in number of bytes.
Yeah, numbers of bytes. You can see the size of key size is 16 bytes, or the
Okay.
record pointer size is 8 bytes.
Okay. So the maximum block pointer and key pointers may be same, but the sizes are different. So we
Yeah,
got to have both the lines. Okay, got it.
yeah,
Thank you.
yeah. Key and the record pointers numbers of will be the same,
Right.
right?
Thank you. Thanks.
So in a real life situation, if I'm storing my keys in random memory, so my laptop has 8 gigabyte RAM.
Yeah,
So the number of address, the size of the address would be, let's say, I can store it in 8 bits or 8 bytes. But my hard disk space is 1 terabyte where
yeah,
I'm
yeah,
storing the data, right? So this will
yeah,
be an example where if I'm storing my keys in random memory, the size address will be of less byte, but where my records are stored in the hard drive, the
yeah,
addresses of that is terabytes, right? So
yeah,
that is will be a situation where depending on where I'm keeping my keys and where I'm keeping the real data in a storage. So if that is where it will be unequal. But I think that part was probably not explicitly mentioned, but that is why the key size may be different because you're storing at different places.
uh,
Thanks, sir. It's
yeah,
clear now.
yes, yeah, yeah. Okay. So everyone clear with this? That
So then this is the main thing. After that, it's just algebra.
yeah, I did not get it. Can you repeat? Yeah. Hello.
Okay. So here, we have a, let's assume that it's a P order B tree,
Yeah, P order battery.
right? So we know that if it is a P order B tree, then maximum number of block pointers will be P.
Yeah, maximum numbers of P.
Okay. And then maximum number of keys will be P minus 1.
Yeah, P minus one.
And and the record pointer also will be, number of record pointers also will be same as key, which is P minus 1, right?
Yeah, yeah,
So the size required to store the block pointer is 8 bytes.
yeah, 8 bytes.
So that means to store P, I need to store P block pointer. So it will be 8 times P,
Yeah, 8 times P.
right? The
Yeah,
next thing is then record pointers.
yeah, yeah,
Record pointer also are P minus 1.
yeah, P
And
minus
each one
one.
of them are of 8 bytes. So I need P minus 1 times 8 to
Yeah,
store
yeah,
all the record pointers.
yeah, yeah.
And the last piece is the, what do you call the
Record pointer.
record pointer? Yeah. Sorry. So I misspoke, right? The key was P minus 1 keys and the key was 8 bytes, but record pointers are 8 bytes. Key source was 16 actually. So we
Yeah,
stored the keys in the end. Okay. So,
and
so
this
that
is
means,
the block pointer,
yeah,
uh, and this is
record
the
pointer, record pointer.
yeah, maximum key, right? Yeah,
So this is where I think I got confused. So 8 is the
a record pointer,
record
and this
pointer, and then 16 is the
yeah, key size.
key size.
Um,
Yeah.
sorry.
So this is why we have written like that. So
Rec-
key is
okay,
16. Yes,
okay.
that's
I'm
correct.
explaining what uh, this is the record pointer size. So this is
Yeah,
the record pointer means record pointer, and this is the key.
keys. Yeah,
Yeah, the key size, right?
yeah, yeah.
So just remember p minus one. What are the, because both are
But
the same, right? P
yeah, so
minus
but
one.
typically in the diagram we go start with the block pointer, then go to the key, go to the record pointer.
Yeah,
So
yeah.
I would probably put 8 into P plus P minus 1 into 16 and then P minus 1 into 8. I mean, to follow a logical sequence from left to right, right?
Yeah. Yes.
So that's why I got a little mixed up.
Oh,
Yeah,
yeah.
yeah,
So you can also write like that,
right, right.
because both will be the same,
Yeah,
right?
just for our, to
Uh,
maintain.
yeah,
The good news is the number of keys are always equal to number of record pointers. So I can always say P minus 1 times what is the size of my key and what is the size of my pointer. 16
hi,
plus 8 also I can do
hi,
because,
yes.
yeah. So, okay. I
So
think
if
then
you
after that, straightforward.
if you solve, I think it will get 17. So you
Yeah.
can solve it. So maximum what are possible is 17.
Okay.
I got 32, sir.
You got 32. Okay, let me
24,
solve then.
24 plus 8,
Actually,
32p
31.25. So do we round it up or do we round it down?
down. This
And
one
down.
down
Less than equal to.
less than equal to.
Yes.
Yeah. So I think okay. 8p plus 8p minus 8 plus 16p minus 16, right? So 8 it's I think 32, right? 32p less than equal to 1024 minus 32, right? So if you calculate, let me calculate.
So it's 2 to the power 5, the other one is 2 to the power 8. So yeah.
No, minus
shouldn't it
24.
take
1024 minus 24,
Yeah,
not 30.
it will be plus, right?
yes,
Plus
24.
24, sir.
Plus
24.
Yeah,
plus
24.
24.
Yeah, 24. So
1048.
yeah, 1024 plus 24 and divided by 32.
32. So it's giving about 32.75. So it will be 32 then.
Yeah, it will be 32. So up to that is clear. So we'll move to the B plus T
Yeah.
then. Okay, we'll move to the B plus T. So in B plus T, order of the leaf node and order of the internal nodes are different, right? So first we'll see uh, order of the internal node, then we'll see the order of the leaf node, right? So order of the internal node is like that. This is the structure of the internal node, and the structure of the leaf node is different in B plus T. So this is the block pointer size, and we only store the key, not store key pointer, right? So in B plus T, in the internal node, only store the key, not not record pointer, right? Record pointer. So it will. This is the block pointer. This is the key, like that. So you can see it like that. This is the key. Then this is the what is the block pointer, BP. Then this is the block pointer, and this is the key, like that. And like K1, K2, KQ minus are the key within each node. This will be the ascending order, and the PB1, sorry, PB2, PBQ, these are the block pointer, right? So while in B plus T, we store record pointer in the leaf node. So all the whatever the records is present, or whatever the keys is present, we store the key pointers. Sorry, we store the record pointers in the leaf node. So we'll see the leaf node structure. So this is the internal node structure, and this is block pointers, and then this is key, and like this is block pointer, and this is key, like that. So internal node structure is clear for everyone.
So basically, you have a pointer and a key.
Yeah. So we'll store like.
So earlier we were dividing this node into 3 parts. Now it's 2 parts.
It is B plus T in the internal node. This is the internal node. There are structure of the internal node, and the leaf node is different. So this is the structure of the internal node.
When you say internal nodes, sir, it doesn't include the root node, right?
It include the root node.
It includes the root node, is it?
Include the root node.
Okay. Yeah. And it doesn't include the leaf.
Yeah, this does not include the leaf. Okay.
So a single order B plus tree would just have one block pointer and one key. And if it's a 2 order B plus tree, it'll have 2 block pointers and 2 keys. Is that it?
No. So I will discuss about that. So if it is the P order B tree.
So if you could draw the B tree and the B plus tree side by side, it will be like easy to identify what's the difference.
You will see when I will insert the B plus T, you will see what is the difference between the.
So I was thinking of a real life example. Let's say the the record pointers are the fruits. So in case of B tree, you can have fruits at the bottom of the tree, like where you're standing on the ground, you can pluck them, right? And also the fruits are available on the middle of the tree. You have to climb the tree. But in case of B plus tree, all the fruits are on the lowest level. So you
Yeah,
can
yeah,
see,
right. Yeah,
right?
your observation is right.
Right. So then
And
it is easy retrieval. You don't have to climb the tree, because if you want to pick up something that is internal node,
and
that
that's
you have to
the
climb.
height of the B plus tree compared to B tree
Yeah.
also less. So
Right.
that's why
Right.
searching is it's easy.
Right.
Then
Yeah.
so yeah. So if it is P order tree, P order B plus tree. So for each node maximum, for each node I am talking about, for each node maximum child pointer can be P. The maximum numbers of key equal to P minus 1. You can see that if it is the P order tree, suppose it is the 3 order B plus tree. So this is the block pointers and the key, again block pointer, again key, again this is the block pointer. So you can see that 3 block pointers and the 3 minus 1 key. So 2 key, right? So this is clear for everyone.
So
Yeah,
this
sir.
is
Till
not
here it
having
is
the
similar to B tree.
Yes, not similar because
record
in,
pointer is not there.
record pointer is
Okay.
not there.
Right, right, right.
Yeah. And we'll see about the leaf node structure. Okay. So like that. So consider the leaf node structure P order B plus T, like Q less than equal to B block pointers. So this is the key and corresponding the in a leaf node record pointer will be there. This is the key and the corresponding record pointer will be there. And at the end of that it will another one block pointer, so record pointer, it point to the next node, whatever the leaf node present, so it will point to the next node, right? So maximum numbers of key, if it is P order tree, maximum numbers of key will be P minus 1 and maximum record pointer will be, this is the, so whatever the record pointer size will be equal to
P.
P minus 1, right?
What
And the
about the last one?
one extra,
Yeah.
you know, child pointer or block pointer, it will point to the next node. That's it. So this is clear. B
So
plus tree.
this happens only in the leaf node, right?
Yeah. This will
Okay.
only happen in the leaf node, because in B plus tree data is only present in the leaf node, not the internal node. In B tree data is present internal node or leaf node also, but in the B plus tree data is present only in the leaf node, only in the leaf node. So we'll see when we insert B plus tree. We'll see with the help of one example. So this is clear.
So then the orders for the leaf and this thing can be different, you're saying?
Yeah. This will be the different. So we will see with the help of one example. Don't worry. So let's insert. Okay. And this is the let. Okay. So see, maximum numbers is 4 order tree. So maximum numbers of child pointer, it is order
4.
4. Maximum numbers of child pointer equal to 4, right? No.
Yes, sir.
And maximum numbers of key,
3. 4 minus 1.
yeah, maximum numbers of key. And the you can and please remember minimum numbers of child pointer or block pointer.
N minus 1
No,
by
no,
2 is
I'm
clear.
talking about pointer, child pointer. n by 2.
Right.
Yeah. So up to this is clear, this point. Hello. Hello.
Yes, sir.
Yeah. Okay. So when you insert 1, so like that one, it will insert, it will point to, this is the record pointer, right? It will point to the next. When you insert 4, so 4 and the record pointers. Then after the insertion of 7 and the point to the record. While you insert 10, right? So when you
It
insert
exceeds.
10, so you can say that it is overflow bucket, right? And the one, remember one point, in the whatever the left subtree, in the B plus tree, whatever the left subtree, it is strictly less than. So suppose there is a, this is y and the, like that. So this is the x. So y will be the strictly less than, right? And z will be, it is greater than or equal to. Hello.
Yeah.
Yeah. So when will be the insert in the 10? So 1, 4, 7, 10, right? Okay. So and remember when we are splitting, so in the left tree n by 2 will contain. So it is 4, right? So it is 3 order, sorry, 4 order tree. So n by 2 will be the 2, right? 4 by 2 will be the true. So n by 2 will be the key value will be present. So 1 and 4 will be the present in the left side tree. So when we what will be the structure? 7, then 1, then 4, then 7, then 10. This is clear? How we split? Splitting is the main thing.
Sir, I could also take 4 up and have 1 and 4 up and then 7 and 10 down, right?
So yeah, see, when we will do 4 up, then 1 down, 4, 7, 10. So we have discussed left subtree. Left
Sir, why
subtree.
are we bringing 4 down? I mean, 4 is already up, right? I mean, I'm getting a little confused
Okay,
here.
okay, yeah. I'm explaining one second. So that will be better. So see. So when you insert 10, so this plus will insert 1, 4, 7, 10, right?
Yes, sir.
So this we have to split. So please remember the left, in the left,
Is always less than, yeah. That
uh,
I,
yeah,
yeah,
in the left subtree it will be the key numbers of key will be the always
2.
n by 2.
Yeah,
So n by 2 will be the 4. 4 by 2, sorry, 4 by 2 will be the 2.
yeah. Yes, sir.
So always present 2 key value. So
Okay.
2 key value 1, 4. It is always present 2 key value.
So we can't take 1. It has to be 2.
Yeah, yeah. We
Okay.
can take, if you split into 4 in this place, this will be 1, right, in the left
Yes, sir.
subtree.
Yeah.
So you have to please remember this will be the n by 2.
And that
So
criteria is not very important for the right subtree, right?
yeah,
It's only for the left one, right,
yeah,
sir?
you have
Okay.
to see in the left subtree.
Okay, sir.
So 2 value. So if we split into the 7, we can say that 1, 4, 2 value is present in the left subtree. So we can easily split, right? So 7, 1, 4, and the left 7 and the 10.
And
So
now why that 7 again, sir, down? That is what.
because all the I've explained in B plus tree, um, all the record pointers are in the leaf node, right?
So this 7 is basically the record pointer. Okay. Okay,
7
sir.
and the corresponding record pointer.
Yeah, yeah. Got it, sir. Yeah. Thank you.
Yeah. So up to that is clear for everyone.
Yes, sir.
Then okay. Then when 17, 17 will insert in that place, because maximum numbers of keys be 3, so does not overflow bucket. So 7 and the record pointer. So up to that is clear.
Yeah, up to 3 you can store, no problem.
Yeah. Okay. Okay, so when will insert 21, so when we will insert 21, it is greater than 7, it is greater than 10 and greater than 17, so insert in that place, right? And this is the overflow bucket, but we have to split. So n by 2, 7, 10 will be the, when we split, 7 and 10 will be the left subtree, so you have to split from 17, right? So how will look like that?
7 comma 17.
7 comma 7 17, like that, and this is the 1 4, and that place 7 10, and this place 17 21, right? And this will point to the this, and this will point to that, like that. And always remember this point to the null. Up to this is clear for everyone.
Yeah.
If you if anyone did not understand, you can tell. I will explain once again, don't worry.
So this is very nice. It is sorting the data and then also putting like groups and then also telling us where the next set is.
Yes, yes.
So very nice. So as we enter new records into the relation or table, we'll start making arrangement. Very nice.
Okay, so while you insert 31, so in that place 31 will insert, like, and this will point to the, so when you insert 31 like that, 31, and this present to the null, because 31 is greater than 17 and greater than 21, so 31 will be inserted in that place.
So where is the 1?
So this is 1, right?
Where? Oh, the okay, it's not 10, 1, okay.
This is the record pointer.
Record part, right.
Yeah, record pointer. So up to that is clear. If you did not understand, you can tell. Okay, and now insert 25, right? So it is greater than 17, but greater than 21 and less than 25, so it will be inserted into 25 that place. But we can see that this is the overflow bucket: 17 21 25 31, so we will be splitting from that, right? So 25 will be go up, right? So when 25 will be go up, so it will be like that: 7 17 25, it is less than 1 4, right? 17 7 10, and the 10 17 21, and the 25 31.
Okay.
Sir, in the normal binary B tree,
Yeah.
when we had 4 keys, we could identify from the middle two which one to pick. But in this case, it's always the right one we pick because of that
Yeah.
two
Yeah.
constraint we have, right, sir?
Yeah. It will be.
Okay.
So in the left, please remember left subtree, it will be the n by 2.
Yeah. Yes,
So
sir.
it
Because
is
of
the,
that constraint, yeah.
if it is the 5 order tree, so 5 by 2, so it will be always 3 keys in the left subtree. This formula, please remember, n by 2. That's it.
Sealing up n by 2.
Yeah, sealing up n by 2. So up to that is clear.
Yeah. Now I think the top one, 7 17 25 is saturated, right?
Yeah.
So next time something happens, then we'll do something.
Okay.
Well, it will happen now.
Yeah. So when we will insert 19, so when we insert 19, so it is greater than 17 but less than 25. It is greater than 17, so 90 will be insert in that place. So this is clear. So 90 will be look like that. So up to that is clear.
Yeah.
Okay. So when
Now,
we'll insert 20, right? So it is greater than 7, greater than 17, and the greater than 17, greater than 19, but less than 21. So it will insert like that. So, but it is overflow of bucket, right? 17, 19, 20, 21. So it will be split in that place, 21, 20.
so
So
20 will go up.
20 will go up, but you can see that 20 will be, it is also overflow of bucket, right?
Right, right.
So then 20 will go up, right? So what will be that?
So
20,
top will be 20, and below that will be 7, 17, and
7, 17. Then this will be the 25,
yeah.
and this will be the 1 and 4, and this will be the 7, 10, and 17. That will be the 17, 19, and 25. This is the left will be the 20 and 21, and right will be the 25 and the 31, like that. So insertion of B plus T is clear for everyone.
Sir, in this case, if our data, in this case, how many? 1, 3 plus 3 is 6 plus 3, 9. So we have 10 tuples,
Yeah,
right?
10 tuples.
Right. So in a binary tree structure, which we learned last week, the
Yeah.
height of the tree was, if it was binary, it was log 2 n. Because now we have a block size of p, like p order, so we can store p minus 1 on the leaf node. So it is n divided by p minus 1, and then I can take log of that with the base of p.
So,
That will be the height of the tree.
yeah, so I will, I did not share about the what will be the height of the tree. I'll tell.
Okay, sir.
Yeah. So insertion is clear for everyone. Okay.
Sir, I want to summarize actually.
Yeah.
So if you could go back to the last step once again, I mean.
Okay, this is step. Okay.
Yes, sir.
I
So
will.
we insert 20 and.
Okay, so let me erase and I will tell. Okay, so when you insert 20, right? So 20 is greater than 17, but greater and also greater than 19. So this will place 17, 19, 20, and 21. So it's because this is the overflow of bucket, so split 20, right? So it will go up. So it will go up, right? You can see that this root node also is the no, overflow of bucket. Sorry, overflow of bucket. So 20 will go up. So when 20 will go up, so it will be in the left subtree 7 and 17, 7 and 17, and the right subtree will be the 25, right? 25, and the left subtree of 7 will be the 1 4, right? This is the 1 4, and the uh, middle of the 7 and 10, right? This is the 7 and the 10, right? And the right subtree will be the 17 and 19, 17 and the 19, right? And the left subtree will be the of 25 will be 20 and 21, and right subtree will be the 25 and the 31. It will be like that. So this is clear.
So the 70, why couldn't we put the 20 and 21? Okay, it could have only 3 children. Okay, fine, sir. Yeah. Clear, sir.
Yeah. Okay.
Sir, in leaf node actually there is a pointer from one block to another block, 1, 4 and 7, 10.
Yeah.
And, there is no block pointer in leaf node, right?
The in leaf node there is one only block pointer. It will point to the next node. This is the block pointer. It will point to the next node. in the leaf node, and this last leaf node it point to the null.
Now I can understand Weber-Smith's analogy of the fruit tree.
Yeah.
You have to wait to be.
Yeah, I had to wait to
Yeah, I
understand.
mean, it's like it's a tree, so like just for the easier in the mind, like fruit
Yeah,
here, and data is the ultimate thing that we are trying to. The entire thing is to retrieve data quickly, right? That's the
Yeah,
main
yeah, yeah.
interest.
Searching is
Yeah.
okay.
I think we started with a single tree. Now we ended with the forest. We do not know how which tree to pick for what.
Actually, that's what it is, right? So these on the terminal, you know where to go. Which tree you are looking for a fruit called kiwi. You know you're going to get it in New Zealand. You know that, right? If you don't know that, you'll start. You go to United Nations and you say, okay, I have to go to the Australian subcontinent. Then there, so all these intermediate structures are actually okay. Which part of the world you need to go and all that kind of stuff, right? So and if, because when you have too many blocks on the bottom, even to search the right block also, you need to be efficient. I think that's the right from the root till you go to that leaf node, how to also go there very quickly. So
Yes.
all these B plus structure is helps us to go there faster compared to a binary
Yeah, yeah,
tree.
yeah, yeah,
That's the difference.
yeah, yeah. Okay, so uh, Pradeep, you can start hashing part.
Okay. Okay. Hello, everyone. So let me share my screen. Okay. Is it visible, right? My screens.
Yes, sir.
Okay. So now we already understood that B plus tray and what is the depth of database persistent storage of also. Now we will see the hash and we use the hash. So in hash, we will see the static hashing and the dynamic hashing and also see the bitmap indexing. That is the important one. So in this slide. So hash is nothing but you can say like the function. You already know the function, right? So, okay. Right. So suppose there is a set of value. You have suppose a set of value like 40. Let's take a 40, 42, and 73, 55, and 97, right? And your hash function, this is your, suppose this is hash function, and hash function equal to, suppose whatever's the value in x, that is modulo 10. So this is hash function, and you have to map to a certain numbers of value, right? That certain numbers of value is called the bucket. So suppose you have defines the 10 bucket, right? So so this is your bucket 1, bucket 2. Suppose whatever this hash function return, if this hash function returns 0 value, right, this will go to this hash this bucket. If 1, so go to this bucket. So similar like that. 3, 4, 5, 6, 7. Okay, let me write here. And this is only, this bucket is possible if 10 numbers. So these are the modulo 10 is possible, right? So if I want to insert this value, these numbers of value, suppose this is, let me write this as 48, 19. Okay, this is a set of value, and this is your hash function, and this you want to map to this particular fixed number of bucket, and this could be many more numbers, as many as possible. So this is based upon the user, right? So can you tell me, this is 40, so hash function is x modulo 10, so what is the value of that? H,
4. 4.
Zero.
that is 0, right?
Remainder.
Yeah,
0.
modulo.
Yeah, okay.
Yeah. So this then 40 will go to this search key value will go to this particular bucket. Fine. And if we do for the 48, then what is the modulo 40?
8.
8. Then it will go to this bucket. Okay. And similar to 73, if we do, that is 3, then 73 will go this bucket. Then 55 will go to, because 55 modulo 10 is 5, then go here. 97, similarly that, right? 19 will go here. So you may have a confusion, what is bucket? Bucket is a, you can understand like this is the block in your database. So whatever search key, suppose you calculate, this is your search key value, you want to store that value in this particular block. Based upon this, you define also best suited for your application. So whichever has function that is under your control, whichever is the best means we will see what is the best hash function is also, right? What are the properties?
Sir, also in particular table, if there is no numerical attribute, then we can't do any hashing, right?
Yeah, you can define for that also. So how you go like to that, already said this hash function is under your control, how you define this hash function. So in this slide actually it is given. So you want to say this one, right?
Okay,
Hello.
right.
Yeah, I will explain that also, why this is like this. So
So
okay.
in the previous one, we took modulo 10. We can take any modulo, right?
Yeah, that is, I already said, this as function is under your control, how you want to define this as function.
So if the data is numeric, you can do modulo. If the data is text, then you have to do like a label encoding, like what you showed.
Yeah. So how you want to define, so that is, I will show one example, then you can understand or relate it to you. So let me define first what is hash function. So hash function is your h, like this one, this is your h hash function, and this will, here you can see this particular search key is mapping to a fixed number of value, right? Any numbers of value here, maybe one, right? This you can also map using this function, right? That is 1, so this will go here, right? Similarly, any numbers of value, 1 to 8 modulo 10, so this will equal to 8, right? So here you can put here, right? Got it?
Yep.
Yeah. Okay. So let me read out this. So a hash function h maps a data arbitrary size from domain D to a fixed size of value, whatever I have done. So this is the arbitrary size of values. Then you put that value to a fixed size of the, so fixed size means there is a 10 size I already defined using this function. So I map to this particular fixed number. So it will be easy for me to search only this 10 value, right? Only 10 this bucket. Okay. And whatever you get the value, that is called the hash value, hash code, and digest, and also simply hashes. So whatever you get, suppose this is your hash function, right? X modulo 10, so that is your hash function. So if you done hash 40, that you get the 0, right? So this is called the digest or hash code or hash value or hashes. This value is called, okay, right? So now you can see, then one more point, if for two key values that is not equal to the key values and the hash value is same, then we can say the collision is occur. Okay, let me tell you what is that. So here you can see 42 modulo for, not 42, 48 modulo 10 is 8, and 1128 modulo 10 is 8, right? So this, if I defines the each bucket can contains only one value, right? Let's assume it is possible only one bucket can contain one value, right? That I have means you have to assume it. So here you can see 42 is this 8th bucket. This bucket is already occupied by 48, right? So if I want to insert this value 1128 into this particular bucket, so here you can see this is already filled, right? So how to, and when you want to insert this kind of you can say this kind of condition or situation occurred, so this thing is called your collision. So this is actually collision, right? Okay. This term is called the collision. So here you can see for the two keys that are not equal to but hash value is same, so that is called the collision. So how you can handle this type of collision in the hashes, then that will see there is different technique how we can handle the collision, right? This type, how to
So
handle it.
basically, our objective is to get a unique value for each, a unique hash value for each of those values, right?
Yeah, basically. So why we do that? So here you can see complexity for the searching is O1, right? In the best case scenario. So if I want to search 55, so can you tell me if I want to search 55, which bucket I should go?
Bucket 5.
5, right?
Bucket 5. Yeah, exactly. That is O1, one shot, right? If I know the key, I already finds the bucket. That is a, right. That is the O1 case time. So this is the best case for searching any searching. You
And
get
when there's a best, is there a worst case also?
yes, maybe possible. So every value, if every value, so let me, before go to that, let me tell you how we can handle the collision, right?
Okay.
So if all the value is come to a fixed set of value, so let me, I will give that also, that example also. So here you can see the next point is the hash function should be collision free and the first. So you have to define the hash function. So how you can define the hash function that need to be minimum collision and it should be first. So
Sir, how many data can be in one bucket also we can decide?
yeah, that is based upon your block size, or you can define also for one bucket how many block you allocate, right? So if you are a developer, means a database developer, then you can do that also. And operating system, that is also by default it is available also. So both type of, so by default you know that the default is size is this, or if you are a developer then you can do that also.
Okay, right.
So yeah, this is already search key and this is hash function and this your bucket. Okay. So bucket is a nothing but that container any or this block, as I already said. So using this hashing, you can store the organized file in the secondary storage also. So you can also define some hash indexes also, right? And that is similar to that what I already explained. So okay. So now come to this one. So there is a one small mistake is here. So this is not 10 bucket. So this is your 8 bucket, right? And this is also 8. Now you can understand. So before going to this example, let me tell you. So what is this? The hash file organization of instructor file using the department name as key. There is 8 buckets, and the binary representation of ith character is assumed to be an integer, and the hash returns the sum of the binary value character and modulo 8. Okay, right. So what it means, so if A is your letter, then you have to take 1. If B is the letter, then you have to 2, C 3, D 4. Right, like this. F G 7 G 12. 14, 15, 16, 17. Okay, I hope I made mistake somewhere. 7. Oh, okay, sorry. So this is 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Right. Okay. So now if we take the music, tell me M value is 13, right? 13. U is 21. S is 19. And I is
9.
9. C 3. Then sum of everything. Okay. Tell me what is the value of that?
34, 53, 60 to 65.
Okay, 65, right? And 65, if it is given the modulo 10,
65
right?
modulo 8. 8 will
So,
be 7.
so then it will be 5. So that's why I said this is the modulo 8, right?
Yeah.
So if
Why
we
is the
take,
why modulo 8? Why not 10?
so because it is a mistake, you can say. If we takes the 65 modulo 10, that will be 5, right?
Yeah.
If we takes the modulo 8, so then
be
it
1.
will be 1, right?
Okay, okay. So 5 is not allowed, is it, sir? I mean,
Why? No, this will not match that way. Not allowed. Not. So this will, I want to match this thing, whatever's the written here. Got it?
oh, okay. You have to match the music, H music. Okay, got it, sir. Yeah.
Yeah.
Fine, sir.
So
Also,
you can
sir,
check similar way here
okay,
also. This value
okay.
is also. Then you got this one. Sum up every value. Suppose what is the position value of 8, what is the position value of I, and as similar
Fine, sir.
way, then modulo 8, you got this too.
Okay, sir.
And so
Also, sir,
similar.
the indexing of ABCD that needn't start from 0. It starts from 1 itself.
Yeah, it is given the ith. So
Okay.
ith character
Be
is as
integer.
I integer.
Okay, fine, sir.
Yeah.
So we are doing letter encoding, and then the word consists of letters. So we are basically mapping each letter in the word and then summing up all the all the hashed values of the letters,
Yeah.
and then applying another function, composite function, right, to get to the final answer.
Yeah. Our hash function is the hash function is divided like that. Whatever's the position value of M is, then you sum up that and the modulo 8.
Got it. Got it.
So here you
And
can
and here we
yes,
take it as case insensitive, right, sir? I mean, there's no
yes,
lowercase,
yes,
uppercase. Yeah.
yes.
But that isn't been mentioned in the question. We assume it to be like that, right, sir?
Yeah, it is given here, so that's why I assume that. So
Okay.
in the question, you do not assume like this question. This is a very silly question.
Okay, sir. Okay.
So here you can see music is placed in bucket one. Similar way, if a history, what is the position of history, that is second. So if any instructor has from the physics history department, that is placed in the bucket 8, bucket 2, and similar for the 3, hash value is 3, then you have to place here bucket. So here you can see in this bucket is a, there is 4 position you have to fill, right? So right, only 4 position is there, right? Now we will see what is the ideal hash, right? So this is the worst case. So same hash value you have to map, or one may be possible every whatever you want to done based upon the this hash value. So every hash value is one not every key has the same hash value, then you have to map to the same bucket, right? So that is the worst case, right? Like is the previous case in the previous case.
So if we take that static, if we say modulo 10, and we select all the values are 11, 21, 31, 41, 51, let's say, then it will be the worst case,
Yeah,
because
yeah.
all the numbers will get mapped
Okay.
to the same bucket.
Okay, can you say that number once again?
So let's say our hashing function is h of
Modulo
x,
10.
yeah,
Okay.
x modulo 10. Let's say the one that we are discussing. H of x equal to x modulo 10.
Okay.
Now we have a set of numbers 11, 21, 31, 41, 51, 61.
31 and
41, 51, 61. Yeah.
41,
All number
60.
ending, any number ending with 1. Right?
Okay.
If this
So
is our
this
set,
is, yeah,
yeah,
this is bucket 1, 2,
0 to 9. Yeah.
5, 6, 7, 8, 9. And this is the only one bucket can contains one value.
Right. So,
Right. Yes.
sir, we talk about the movie theater example, right? So let's say this is a movie theater. Movie theater has each of these seats are like uniquely defined. Only one person can sit in a chair, right?
Yes.
And let's say I create a hashing function at the assume that everybody has bought a ticket. I ask people their Aadhaar number, and I take the last digit of the other number, and based on that, I allocate them a seat, right? So what happens is the first person, no problem. If the second person's other number, last digit is exactly same as the
21.
first number, then we have a problem. That's called collision. Now we have
Yes.
two people trying to make them sit in the one position. So that's a physical analogy I'll give, like movie theater, so that
Yes,
way
yes.
at least easy to realize what's really going on with the collision here.
Yes. So what happens? So if we calculate this one, hash value is 1, right? So you can insert directly this position, right? 1. And what happened if we find the hash value of 21, that is also 1, right? So you want to insert, you have to insert into this position, right? So that is, so you cannot insert because only one position is available. So how we can handle the collision? So there is also there is a procedure to how we can handle collision, right?
So
So
in hostel we have, right, bunk beds, YMCA hostel.
yeah. So there is a one is the closed racing, and another called the open racing. In the closed racing, what happened? You can create another node, right? Let's create new node. and you can attach with this particular position, right? Like this 21.
So,
Again,
so many parking lots in the malls have that, right? So nowadays the space is a constraint. So you go and park a car and then double deckers, right? So if a second car comes, if the parking lot is full, then they'll move the existing car to the top floor, and then I don't know. Many of the malls also have that now.
if that mall has the same means ground floor and the exactly at the same positions, the first floor is also same position, same means well in the same value means first position in the first floor first position is available, then you can relate like this.
Right.
Yeah. And then you understand this, what is the closed dressing. Closed dressing means you create a new means new node and attach to with this particular index, or you can say with this bucket. And again, if you want to find the hash value of 31, then it is also one, create another new and attached with this, right? And this is the worst case because every value have the same hash value, search key has the same value, right? Similarly 61, so you can attach the 61. This is one approach of handling the collision. So that is the closed dressing, we call this is the closed dressing. So another is also possible, another way possible. So that is the open hashing. So open hashing ends if this position is not available, right? For this one hash 11, that is the one value you put that in this one bucket, and if 21 come, then hash value is 21, then you can put whichever the next available space that is here, right? So you can put here, and if 31 come, so you have to put here, and the 61 you can put here, and 41 similar, and 81 here. But here you can see the problem is that you cannot actually whatever you define, you actually not follow that one. So if I got the 22, right? So hash value of the 22 is 2, because 2 position is not available, so you have to put here. So you kind of what you actually defines that you not maintaining that things.
So in this case, the searching would be difficult, right? If we have to
Yes,
search
yes,
for a key.
exactly.
So you define a rule, but you cannot break the rule every instance. Then basically,
Yes, yes. That
right.
what
So
is the
then,
point of that rule?
what's point of having a rule, right?
Yeah. So that is the problems with open hashing, right? That's why in the database we only prefer this closed hashing for the database application, closed hashing, right? So it is a much more simpler way to handle that collision. Okay, got it, right? What is so? Yeah. So what is the ideal hash function? So ideal hash function should be uniform. Whatever you based upon your data, you have to choose your hash function so that it will uniformly distribute the data. Means each bucket get at least the same or around the same numbers of key from the all set of values, right? So that is one characteristic of the ideal hash function, that should be uniform, and the ideal hash function to randoms. So you cannot say like that if in this hash function if you give the value in the order manner, then this hash function is uh, means work properly, right? And if otherwise if cannot say like if you gives in the descending order, it will act means it will work properly, right? So you can user can gives the data in any order, but your hash function responsibility is that it will distribute the data among all the bucket. So that is one condition of the ideal hash function. So these are the two property. One is the uniform and second one is the random. So that is point here. So each bucket will have the same numbers of record assigned to it, irrespective of the actual distribution of the search key values in the file. Right. I hope it is clear what these two terms.
Yeah, they are ideal properties of good
Yeah,
hash function.
yeah. Because hash function definition is based upon you can define the hash function. So it so okay. So why the we already discussed the bucket overflow is what is bucket overflow, right? So why it happened, right? So because of the insufficient bucket, or you can say the bucket size also. If we defines the you can say more number of bucket, or if each bucket contains the more numbers of record, then it will not happen, right? Whatever it's, if I defines the 5 or the 10 buckets, each bucket contains the 10 numbers of records, 10 numbers of search key, then it will not happen, so, right? So you can understand this point like this. Okay. And second one is the skew in distribution of the record. So maybe multiple record have the same search key value. We already have seen that. So like it's the 21, 31, 61 have the same hash value. That's why it's going to the same bucket.
So if you look at if your names of students is your relation, right? If you notice the most of the Indian names, a lot of names starts with letter S. I don't know why. Always start. I mean, if you, I mean, I've seen that randomly take bunch of names,
Okay.
do a distribution, looking at the first letter. If our hashing function is, I define 26 buckets, and the bucket it assigned is to the starting letter of the name. You'll see a
Okay.
lot of people. There will be a lot of collision in bucket S. That because there's a skew in the distribution of how we name our
Yes,
stuff.
yes. So you cannot text the name, right?
Correct. But if you go to China, you'll see most of the people start with X and Y, right? But in India, it is mostly S. So there is a general skewness in how people name if you go to the different part of the world. But
Okay.
these are all real life phenomena. Don't know why. So there is a natural intrinsic skewness in the data. So when that happens, then we have a problem. If you're
So
trying to
then
take
you
the
have
index,
to then you have to choose your hash function, means wisely, you can say,
yeah,
or very
correct.
carefully. Okay. And we already see this one, how bucket overflow is handled. So that here it is given, one is the close hashing is also called the overflow chaining. The overflow bucket are chained together in a linked list like this. And open hashing means you can uh, positions that data into the next space where it is available, right? Right. So example of hash indices. So here you can see one example of the hash indices based upon this ID.
It looks like an employee number. Sorry, what is it? Department, whatever.
This,
Okay, this is a faculty probably, right? Faculty ID, faculty name, department, and salary, something like that. Right?
yeah.
Yeah.
So this is based upon this value. So ID based upon this, we sum up this ID and modulo 8. Adding digit. So here you can see. So this is, you cannot assume that like what is the value. It is already given to you what is the hash function. So here you can see compute the hash function, adding the digit. So hash index on the instructor on attribute ID, and compute the adding the digit and modulo 8. So that is 7 6 7 6 6, that is 14 plus 18, 32, right? So that's why it is in the 0 position, right? Or no, 0th bucket, right?
Yeah. We sum up all the digits divided by 8 and put in the remainder.
Yeah. So similar way here, 3, you can see 3 modulo 8, that is 3. That's why here it is. And here also one example of how means bucket overflow. So how we take care of the bucket overflow is also given in this example. Because the bucket size is 2 only, right? Hope this example is clear, right? So this is a one demonstration of the how hash function work. Okay, got it, right? Any confusion? Okay. So now you already got the idea of the static hashing, right? So now I want to discuss about what are the deficiency of the static hashing, right? So static hashing, you can see there is a, you already, before you use the hash function, you already define what is the size of your bucket, right? But in the practical scenario, your database may grow or shrink with the time, right? So you cannot do like this. So if you initially defines the bucket and the bucket is too small, but if the file grows, then your performance will degrade, because you, for compensate that part, you create a lot of means overflow chain, right? So here, whatever's the advantage of the hash function, so what is the advantage of the hash function? You got the data in the O1 complexity, right? But due to adding the bucket overflow, means bucket overflow chaining, so you can see you have to do the linear search, right? You already see in the one bucket, right? So there is a lot of bucket overflow chaining, right? Like this. So you already know this is a linked list. Linked list you cannot do, you have to do the linear search, right? If this value is not available, you have to search here. If it is not available, you have to do. So kinds of you have to do the linear search. So that's why performance will degrade here because of this too much overflows. Right. This point is clear, right? Okay. Okay. And one solution is, you can see, to anticipate that growth. So you can assume that in the future this much space maybe I required, right? I will require that many numbers of space, and you can define that space also. But you can see when is the small numbers of data, so you can see that is the wastage of this space. And if that data further shrink, then also against the space will wastage. So whatever's data you means assigned to anticipate that the future growth, so that also, so this is kind of, you cannot do like this also. Here you get the performance, but you wastage the space, right? In the second approach, you can see, right? So here one solution may be possible. So every time, say, you have to reorganize the file. If you whatever you defines the database, not database, the bucket, right? So if that many numbers of value is filled already, then for to allocate new bucket and reorganize, right, in the new bucket. So what I means, let me check. So if you have the four bucket, right, and already four bucket is filled, right, so what you will do, you will create, it's a double the bucket size, that is 8, and you reorganize the file based upon the new hash function, right? So during this time you cannot search or insert or, right, or delete also. So that means, so it disrupts the normal operation. So you have to abort that time, so whatever's operation you want to do in that database.
So it's actually real life. Yesterday night, I got an email from my bank that they're going to do database maintenance. So I cannot access the database from 12:30 midnight to 12:30 afternoon on Sunday.
Yes.
So yeah, obviously as a customer, I don't like it, but now you have to inform your millions of customers that sorry, we are maintaining our database. Don't
Yes.
log in. Database not available. You can't do anything.
Yeah, yeah. So that is one problem also. So what is the better solution for that? So what better solution, if you can do that dynamically, right? So whatever's to based upon the your data. So if you have any algorithm for that, so it will automatically in the growth of the database, it will anticipate your changes, right? And also if database shrink, then it will reduce the numbers of bucket also. So if it will happens, then it is the better solution, right? So it will done by dynamic hashing. So we will see one of the example of the dynamic hashing. So extendable hashing. So before discuss this one, so this is an advanced algorithm. So before discuss this part, I will want to discuss the bitmap index, right? So bitmap index, it's based upon the bit. So whatever we done in the bitmap index, so that is based upon bits, right? So okay. So when we use the bitmap index, right? So when you have the small numbers of the distinct value in a column, right? So you can, if you say gender, so only two distinct value is possible, male and female, right? And if you income level, or you can say country is only what not country is also possible. It's around 200 country, right, in the world is possible.
Yeah,
Yeah.
200.
And you can say state, if I categorize the IITM student into state, so you can say there is a 29 state is, right? So that is a distinct, you can say that is a means minimum numbers of value, right, distinct value. So here also you can say the income value is also, so you label this income value, this as L1, this is L2, and this range is L4, and this is a L5, right? So you can categorize every salary is come under this level, any of this level. So here you can see that this is a 5 distinct value, right? Then you can use the bitmap index, right? So like the query, let me see where the query is. Like suppose consider this table. So your frequent question is like select star from table. Suppose this table is, let's take the table is name is the instructor, right? So instructor, and your condition every time you fire in the query like this, where gender equal to male, there is only two possible, female or male, and salary is L1, right? So this kind of query, when you want to query into the database based upon this distinct value, right? So these are the distinct value. Only 5 possible is possible. 5 value is possible in this income level, and gender 2 value is possible. Then you can use the bitmap index, right? Okay. Just
So in this case, you have put bitmaps for gender, male and female. How
yes.
did you get those values 100, 10,
Yeah,
and
I will tell that. Okay, just a minute.
So in other words, are you saying that these are good indices where my cardinality of that attribute is low?
Cardinality is not the correct word. So I said that rather than that, distinct value is
Oh
less.
yeah, okay. Oh yeah, okay. Number of unique values or distinct values.
Yeah,
Right.
yeah.
Yeah.
That
Yeah.
is less.
Right. 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 Okay. Got it. And then secondly, in our university database example, we have instructors, we have students, we have enrollments. Also here, what we understand is in database we have to think of search, update, and all that, right? So every semester when it goes, the enrollment table you'll see a lot of activity, but I don't expect instructor table to go through a lot of activity in the sense, yeah, when new professors will join, some professors will leave, but the number of insertions and deletions in the instructor table is going to be a lot less compared to, let's say, enrollment, where every semester there's a lot of activity, students are adding and all that, right? So depending on the usage of the table, whether there's a lot of insertion or delete actions, but it's relatively static, not changing too much,
Yes,
and
exactly.
the number of unique or distinct values are less.
Yeah,
Bitmax index is an ideal data structure for that kind of activity.
yeah, yeah.
Right? I mean,
Yeah, I already said like this. Select a star from index. This kind of queries only, not insertion and deletion. Only read only. Then we, because this what you creates the this bitmap based on this column, so that is kind of fixed based upon this value only, whatever instant is present, right? So if you change the instance, then you have to change the bitmap also based upon that. So
and to reconstruct that will not also much take time because the number of distinct values are less. It can be done in few seconds, right? Because even if the database has like a million, but the number of distinct values are less, so the index is actually only 2 records, right? I mean,
so you can apply that, but that is not the ideal case. So
right,
when we
right.
go to use that, so whenever you want to use something, so you use that is the based upon the advantage of that. So you have to, if you want to, every time you have to calculate for the new one, so that is not the kind of you taking the really advantage of that index property. So that time you have to go to another index for that.
Got it.
Okay, okay, let me, how you can construct this table. So here you can see, first you have to number record whatever's the numbers here present, you have to fix it. So here you can see this is the record number 0, like 1, this. So whatever's the order, that is you have to be fixed it. Then you can define the bitmap based upon the gender, right? So if you want to based upon the gender, so you have to creates the for that distinct value. So m is the distinct value and f is the distinct value, right? So when if you want to create the for m value, so you have to consider in the this order is also same, right? So if you want to create the m for the bit array, so wherever the m value is present, you have to set 1, and whenever the m value is not present, you can set that value as a 0, right? So here you can see m value is present, so you have to give 1. Next value, m is not present, that's why it is 0. next value m is not present, that's why it is 0, right? After that the m is present, then you have to put 1, and m is not present, that's why 0. Similar for f, whenever f value is present you have to set 1, wherever f value is not present you have to set 0.
So basically, the number of elements in this bitmap will be equal to the number of records?
Yes, exactly.
Okay.
So this is your numbers of record, and order is also important. So why important, I will tell you that also.
So it's like a one-hot encoding. I know it's in a different course we studied.
Yeah, it is
It's
a
like a
one-hot
one-hot
encoding.
encoding. Yeah.
Okay, so here you can see f, for f also not f0, f1, f is also present, right? So not f0, 1, right? Similar we have to do for L1. So there is how many values possible? L1, so it is already given, so that's why it is the L5, right? So in question you can see there is 5 numbers of the distinct value is possible, right? So, and already it is a defined, so how it is. So this is L1 value, this is L2, L1, L4, and the L3, and there is one value, extra value, that is not assigned to any ID, so that is L5, right? So you have to do similar way. L1, here you can see L1 is
But how is the bitmap for that constructed, sir?
for L5.
For all of this L1 to L4?
Yeah, I will tell you. So here you can see for this L1 is present, right? Hello. Yes.
Yes, sir.
L1 is present, right? That's why it is 1. Next bit L1 is not present, that's why it is 0, right? We are doing for the L1, you see.
So
L1
it
is
starts
1.
from the left-hand side. So we read from the left-hand side, right?
Yes.
Okay.
Okay. So then 0, not L1, then again L1, 1, then 0, 0. So here you can see 0, 1, 0, 1, double 0, right? So if we want to do for L2, so not L2, 0, L2, 1, not L2, 0, not L2, 0, 0. So 0, 1, 0, 0. Got it. So similarly, you have to do for the L3 also. L3. So L3, this is 0. Not L3 means 0, 0, 0, 0, and 1. So similarly, you can see 0, 0, 0, and 1. Similarly for L4. Right? Not L4, not L4, not L4, L4, 1, 0.
Sir,
Right?
that is distinct and complement each and everything, right?
Yes. So if you define the property, what is the properties of when to use the bitmap? I already mentioned. So this is possible for the distinct, means whatever the distinct value, that is the less number, right? Then you can apply this one. So otherwise it is meaningless if you use for this one. ID is all ID value is a unique, right? So here you can use the primary key index. Now
So
bitmap is,
how does this help in searching
yes,
faster?
I exactly come to that part. So here you can see how it is, means we construct this table, right? Hello.
Right. We got our
Yeah,
zeros and
L5,
ones. We got our,
L5. Yeah, L5, not L5 is present, so every value is L5. Now you tell me what is the query. If I query here, so select the all details of the instructor who are whose gender is who are male and income level is 2, right? So you have to pick up wherever the index value of L2, right? So let me do this for this one. So where gender is female and the income level is L2, right? So your question is finds the details of all the instructor who are female and income level is L2, right? So you have to find what is the bitmap value of female, right? So that is 0, 1, 1, 0, 1, right? And what is the value of L2, right? This one, 0.
Yes.
And
Yeah.
your question is find female and L2, right? So you have to do AND operation here.
So tuple 2 will be selected.
So this AND value is 0, 0. You already know the truth value, right?
Yeah,
Truth value
sure.
of, yeah.
XOR.
So this is 0, this is also 1, 0, 0, and this is 1. So you have to, if you are doing AND, right? Gender is female and income level is L2, right? Then you can do like this. So here you can see only 1. So you can simply say this numbers of record. This record is your desired record, right?
So
This
that
is
0, 1 that we are putting, we are actually putting the record number there. Is it?
Yeah.
yeah,
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 like a tuple in your relation.
yeah. This is the record number, right?
Okay,
So
you're
this,
putting those record numbers there.
yeah, yeah. So that's why I tell. So this is your order is important. So whenever you create the bitmaps, the order is also important, right? So this is one operation.
So basically, sir, you've picked up one from the place where both are one, right, sir?
Yes, yes. So
Okay.
you know the truth table, right?
Yeah.
What is the AND truth table? So if the query is like next one, so this is AND is clear, right? So if your
Yes, sir.
query is like find the details of instructor who are gender or income level is L2, right? Gender is female and income level is L2, right? Then you have to do the OR operation, right? OR operation, right? So you know the all OR operation, right? So OR means 0, 1 truth table is 1, right? For or cell explains the truth table of OR.
So any one has to be satisfied. So if there
Yeah,
is a
yeah,
one on either row, it will be one. Otherwise, it's
yeah, yeah,
zero.
yeah. So this is 1 and this is 0. So you can see this tuple is satisfy the condition, this tuple is satisfy the condition, and this tuple is satisfy the condition. Then you have to pick up this row or this record, right? So this is the easy.
Easy method when we don't have any new instructor joining. So the moment the university hires a new instructor, then our bitmap
Yeah, yeah.
has to
So
be updated.
yeah, yeah.
Any
No,
one
so
of it.
even that, Devasmith, even that would fall under the same bitmaps because it will
No,
be
no,
either
no.
gender.
Well,
Yeah.
not on the Fed. Let's say we add record number 5. Let's say we hire a new instructor. Then our bitmap will be not length 5. It will be 6 now. So
Yeah,
everything has
then
to be
length will
reloaded.
change. Yes, you're
Yeah,
right.
yeah. So you can say that that is the not good idea to implement the bitmap there.
Correct. So that's what we said. It has to be static.
Yeah,
Two
yeah,
conditions. The table is static plus the number of unique or distinct values for that attribute is low in number.
yeah, yeah.
Right.
So here I summarize that this is the static table size is the static. Second is the read only, means you only read the operation, not you want to insert or delete, right? So this time we prefer the bitmap. So first one is the static, table size is static, and we also performs the read operation. So read operation means only select star, like this kind of operation. And second is the whenever the distinct value is less.
So I don't know if people are working professional in a real life application in a business. we have this online transaction database, then we have something called a data warehouse, which follows a different schema, what we call as like a star schema. So we have dimension tables and fact tables. So this is an ideal candidate for data warehouse dimensional table, where it is fairly static and you only read, and the number of distinct values are less for that
Yeah,
dimension table.
then you can use that.
Yeah.
So
But there also it becomes, you have those slowly changing dimensions.
Type to type. That's what I said. That's slowly changing, right? That's why type to type 4, right? So yeah, but that's an ideal case for bitmap.
So I hope it is clear, or how or operation, or you can say finds a instructor whose salary is L1, right? Then you have to simply perform, this is the salary L1 instructor. So you have to fetch the record first one and the third one. So this one and this one, right? This. Or
So question here. So you're saying it is your gender and income, okay, they can be small, but your instructors can be in thousands, right?
yes.
So then your bitmap will have at least 1,000 bits, right?
Yes, exactly.
So there'll be 1,000 at least values in each of those levels.
Yeah. So here you can calculate the what is the, if your original table size, or you can say database size, right? That is means greater in number. The table size is large. Whatever. So
Right.
if you uh, the measurement unit is MB, then it is in MB, or you can see in the GB. But if whatever the table size, index bitmap size is less than that, very much less than that, right? So you can calculate the size of bitmaps also. So let me ask you a question. So can you tell me, what if you are doing the bitmaps based upon this, based upon income level, right? Then what is the size of the index file of the bitmaps? So let me refresh that. So what is the file of bitmap index? What is the size of file bitmap index? So if you done bitmap based upon this income level,
3 bytes. 3 bits.
how?
The number of distinct values are basically 5.
Okay.
So I can represent 5 numbers using 3 bits in a binary encoding system.
Okay. No, that is not my question. How to? What is the size of index
The index file, basically the
file?
size of the index file.
Okay, so then the number of records.
Numbers of records, and also this is matter,
Correct.
right?
Yeah,
How
n
many
cross p.
distinct value?
Correct. N cross p basically. Yeah.
Yeah. If
Yeah.
this is the n, this is the n represents the numbers of record,
Right.
right? And distinct value represents the p. P
Right.
represent your numbers of distinct value.
This
No,
is reminding us of MLF now, right? Yeah.
And
numbers of
uh,
distinct.
but again, how do you get the size? Now,
Yeah.
fine,
Let me. Yeah.
you've got
So
your n records. You've got 5 records here,
yeah.
right? And your levels are also 5.
So this is 1 bit. This is bit. So you already gets that data in bit, right? So 5 into numbers of record is also 5.
Yeah.
So you got 25 bits, right, to represent this index file. So bits, you can convert 8 bits equal to 1 bytes, right?
Okay.
Hello. Yeah. Now you can convert that, right?
Sir, that 5 into 5 is because of this. You have 5 indexes, and then you have 5 records. So that is 5 into 5, right?
So now it will be clear to you. You got this one. So this is the numbers of records. So this is the generic n into p, numbers of the distinct value. Now you can tell me, this is the original index.
It's a record pointer, right? A pointer, size of a pointer. What is the size of the pointer? Because
No,
it
I
is not
am
just
not
a bit, right?
asking the size of the pointer. I am asking the what is the size of the index file. So you want to store this index in a file in your means
Yeah.
storage
But your
system.
index file consists of pointers, right? Record pointers.
Yeah, but sir is not asking pointer size, but rather the file size.
No, but that file itself, when you talk about the size of the file, it is not just 101010, because my 101010
Yeah.
does not mean anything unless that 10 points to something, which means it points to a certain memory location, which is like
No. Okay.
a,
So
a, a, a pointer somewhere. So how do we know that if
so
it's pointing to a
here,
memory location?
okay. So here my question is, so if here you already know that the record number, so record number, this thing means this is, you can understand this as your uh, first block, first data block. 0 represent first data block, this represent the second data block, this is third, this is fourth, and this is the fifth, right?
Okay.
Okay. Now if you got this one, if I asking what is the numbers of what is the details, you have to find the details of all the record that is present, that are from the income level is L1, right? So by default you create this index such that if this I fetch, this is a 1, that means I fetch this record. So this is kind of, you assume that things or predefined it, or you design that index table in this way, right? Hello. So
Yeah,
if
I'm
this
still
is the
trying
set
to.
bit is 1, so then I will fetch this record. Clear?
Yeah.
So you can say this is your database, right? Original database, and this is your index file, right? Hello.
So in this example, the number of tuples are n, and if we are creating the index on gender, it will have only two records because there are only two distinct values for gender. But if we do the index or
No,
bitmap,
not
no?
two records. This value is a represent your first record, this represent the second, and this one is a third.
So what I meant is like index file, like number of entries in the index file. That's what I meant.
Yeah, yeah.
That's what I, yeah. So basically, if my original relation has n tuples, my index file will have two records, and each record would have of dimension 1 cross n.
1 cross.
I mean, sorry, I'm using a matrix or MLF kind of notation. So you'll have two entries. The first, each entry will have size n, which is equal to the number of tuples in the
So
original
you are
relation.
talking about the index file, right?
Yes.
Okay.
So
So
so here original file, if
okay,
you
okay.
take this
Sorry,
data,
1 minute to
if you
interrupt.
take,
You are talking about this index file. There is two index file. One is the index file is based upon this. Okay, let me
correct,
clear
correct.
something.
So let's say, let's take the gender one first, right? Because that's the
Okay.
first one. So
Okay.
original relation has three attributes: ID, gender, and income level.
Okay.
And it is a 5 cross 3 basically, if you are storing it in a whatever matrix or a database, right?
Okay.
5 cross 3 is the original dimension of my relation, but we decided that we are querying too often using gender and income, so we want to create index for these attribute A2 and A3,
Okay.
right? And these are non-prime attribute, because for ID you probably have the primary key and all that, right?
Okay.
So for gender, when we create, gender has two distinct values. So my index file will have, I guess, like 2 entries. First entry would have value 10010. Second one will be 01101. So it's really the number of entries
Index
are
size.
basically equal to distinct values.
So the index size in this case will be 10 bits,
You want to,
right?
I don't
Okay,
know.
in this case, yes, exactly 10 bits.
Right. So each key, so there are two keys, and each key size or value would be 5 bits basically. And why? So why we need five is because we have got five, records. But if we do it in a binary format, I think this is this matching. So that's what it is, right? It can be stored even more efficiently. Yeah, but at least in this example, it will be 2 by 5. The other one, income level, there are actually L5 is a little misleading because it doesn't exist in the relation. We'll probably have four if you go with L1, L2, L, right?
Okay.
But assuming that we missed some of the data, we are not displaying it.
Okay. Let me, if you want to discuss in the details, okay, let me discuss in the details also. Okay, but don't confuse. You got this point, right?
Yeah.
So suppose this is your database secondary storage, right? So this is the block, means whatever's the data. So you allocated this space for the bitmap for the gender one. Here you store the whatever's the file size of this gender bitmap, right? Bitmap
Yeah.
index.
Yeah.
And the second one is the income level. Right. And the third one for this original data, whatever's the index file, right? Not index file, instructor
Relation. Yeah.
instructor relation.
And my ID, which is the primary key, is probably stored in a B plus tree structure.
Yes, that.
So I just want to make sure we combine all the concepts we learned, right? So
So this is the one instructor file. This is your original record you stored here, instructor file. And whatever you prefer for that is the primary index. So primary index is based upon this ID because this is the primary key. And suppose this is the your what you say B plus tree or B tree. So
right.
here whatever's the index size of the B plus tree you stored here,
Yeah.
right? B tree.
Right.
Okay. Now if we look close to this index file, this is visible to this only when you query in your database system, right? But in the deep down into the original database, you can see this is just stored in all the record in the one block. So
Yeah.
suppose this is the you numbers the first block as the 0. So this whole record is consist in this block. Then one block here, this is stored this data, right?
Yeah.
Okay, similar way to 3 and 4. Okay, up to this is clear, right?
Yes.
Now I defines the one index file, that is my index file is based upon the income level. So I bring that into the my RAM, right? Now I query the data like this. If you finds the details of the all the instructor, right? All the instructor who has the level 1 income.
Yeah.
Okay, then you have to look for this one. We already defines the if first record is 1, then we look the data this data block.
Yes.
If the second block is third block is also set, then we see the third block, right?
Yes. Yes.
So in that time, my question is, what is the size of the that file you extract that file here, right, in the RAM? So what is the file of that size? So you already retrieve this file, right? And this is your file size. Index file, bitmap index file based upon the income level, right? So this is the file size. And how
Yeah.
you get that file size? That if numbers of records, this represent what is the numbers of record, right?
Yeah.
There
Yeah.
is a 5 numbers of record. And what is the distinct value of the label one? That is the 5, right? So then is the 5 into 5 bits is required to represent this income label index, right? So that is 25 bits.
Yeah.
That is the size of this index file. And here you can see, if you want to convert these bits into bytes, then you can simply divide it into 8. That is the numbers of bytes.
Yeah.
Okay.
And it's in memory, so you can do the operation that and or very, very quickly.
Yeah. This
Right?
is because 01 computer understands 01. That's why it
Right.
is
So
very fast.
the you can store it in memory, you can do fast computation. So after I do the condition that gender equal to F and income level equal to L1, so we know which tuple number we need, and then
Yeah.
from that tuple we can know which block, physical
Yeah.
block, we need to go to fetch the data. So
Because
that relates
you,
to the previous week. Like, so we'll our the data is stored in those cylinders, it will go and do the seeking, right? So the head will go read and then get the relevant data from that physical storage, right? So
okay, I hope
I think
But
that
so
we
now.
still, I didn't understand why aren't we considering gender here? Is it because it is smaller than that income level?
No, I not ask what is the file of the gender. I only
Oh,
ask
okay,
what
only
is the
income level.
index file, income
Okay,
level.
okay, so yeah,
So if I ask the gender, what
then
is
it will
the,
be 10, right?
then it is the 10 bits.
Okay.
okay.
So this is two different index, right?
Yes,
We
sir.
are, when we query, so we use these two index file together. Right?
And then we do the operation and or condition depending on
Yeah.
what is the SQL on
Whatever's
these
the
two places. Yeah, to
you
narrow it
can
down
do
further.
and operation, you can do or operation, you can do not operation, not, right? Not
In
level
memory.
one,
Yeah.
not level one. You have to unset whatever's the reverse the bit. So you have to 0 1 0 1 1. So you can select this.
So this refers to one of the old tutorials, I think in week 2 or week 3 we had. So we go back to that tutorial to understand this and or not, XOR and all
Yeah,
those things, right, sir?
yeah, A
Yes,
minus
yes.
B. Yeah.
Yeah,
So gender equal to F and income level not L1.
yeah.
Yeah. So this is very simple. If you invest 10 or 15 minutes, you will understand what is the truth value of and, or, and not also, right? And whatever you understand in the sequels, like and is simply you can equivalent to intersect, right? Or is equivalent to union, right? Like that. Hello.
Yes, a big two. We have
Yeah,
already
yeah.
covered that. Yeah.
So I hope up to, and there is a week 5, this 9.5, there is only syntax how you can create that thing in the PostgreSQL. So let me give a little touch for that. So how you can create the index in the SQL. So there is a SQL command, right?
Create index.
Yeah, create. Is it visible color? Let me change the color. So SQL syntax is like create index, right? Index, then index name, whatever's the index name you want to, index name, then tab on, then you have to refer, suppose this is the index, not index, this is the instructor tables, right?
On instructor.
So on instructor, then you have to mention the column name, list of columns you want.
So in this case, will be probably start with gender, right? So
Mm,
create index, maybe IND,
no,
gender.
so you, if you want to create the bitmaps based upon the means, so this is the very generic syntax of the create index. So if you want to create the index based upon the bitmap index, right? So there is one keyword you have to add, create bitmap index. or if you want to create the bitmap index, right? So you have to create bitmap index, index name on, and then you can mention the column name. Suppose that is gender. So this will create the bitmaps. Otherwise, this index will create the primary index list. So here primary index is not, so value is not unique, right? So you cannot create the primary key based upon this primary index based upon the gender, but you can create based upon this column ID, right? So this is one syntax: create index, index name on, then you have to mention the table names, and then you have to mention the attribute name based upon on which you want to create the index, right? And for the multi-level index, you can mention the second column also here, right? So this is how to create the index, and the second one is how you can drop the index. So similarly, that is a drop index command is drop index and then index name, right? Hello.
Yes, sir.
Okay.
So will our OP have this indexing part of it?
No.
It is only as a MCQ which we'll have in the quiz.
No, in OP you can see OP query is based upon your 2 or 3, week 2 and 3,
Okay.
and the Python programming question from there.
Week
There
7.
will be
Week
2
7,
Python
I think.
programming question from the week 7.
What, 2 questions, is it, sir?
2 and 1 is mandatory.
Okay.
And
And
when
if
is
you
OP?
Yes,
27th or
20.
December 6th, one of these 2 dates. So we're going to cover week 2, 2, 3, and 7. Only these 3 weeks, 2, 3, and 7.
Yes, OP in OP. 2, 3.
Yeah,
What about
and
quiz 2, sir?
Quiz to 5 to 8.
So there won't be anything coming from 1 to 4?
Maybe come 1 or 2 question, but not very much.
Okay, sir.
it's going to be a fun one.
Can we look at the this thing practice assignments?
Practice assignment, which one?
Week 9.
Okay, which question can you tell?
See, in practice assignment 9,
Okay.
not graded, question number 3 and 3, 4, 5, and 6. I think those we can look at.
3, 4, and 5. Okay. Right, this question, right?
Yeah.
Okay, so in this question, let me read out. Suppose a data file has 1 lakh records, and each disk block contains the 10 records, such records, and the records are unspanned and the fixed length. Okay, and the total space is required. And the primary sparse index for each block. Okay, and the key size. Okay, you got this question, right? How many blocks is required to store the index file? Okay, so here you can see there is a one. This is your database. So this is your database file, or you can say the main file. Okay, and the second one is your index file. Okay, so index file will store the record of that, and how many records are there in the main file. This many numbers of
You
records.
have 100,000 records.
Yeah, and each block, So here you can see in each block we can contains the 10 records. So this term, if you know these terms, whatever, how many numbers of record can accommodate in one block, that is also called the blocking factor, right? So if you don't know, then you can understand this. So 10 is your blocking factor. So that is the blocking factor, means how many numbers of record you can put in one block. So that is called the blocking factor, right? So here blocking
So that
factor.
was like a order, right? What we studied in B plus equivalent. Because if
No,
my binary binary tree is order P, we can keep only P minus one.
no, so do not compare with that, because whatever you see that in the index file, right?
Hmm.
You once, and I'm talking about the database main file. So
Oh, okay, okay,
blocking file.
okay, okay, got it, got it. This is the physical storage in the
Yeah,
hard
yeah,
drive.
yeah. So that's why
Okay,
I read these two things to
got it,
understand.
got it, got it, sir.
So there is 10, and this database main file size is also
Is 100 MB.
100 MB. Okay. And the sparse index, and sparse index means you already know. The sparse index means for every block in the main file there is one entry in the index file, right? We not put every record into the every record search file in the index file, right? So that is your dense index, right? Whatever search key, every search key, if you want to put that into index file, that is called the dense indexing, right? And sparse indexing is not every value. You put some search key value in the index value, uh, uh, index file, that is known as the sparse index, right? Sparse means not every value, right?
Yeah,
It's
one value for each block.
yeah, each block. So that's why I pointed that one. So this, like this. Okay, so now you have to find the what is the block size. So here you can see how many numbers in the block required. So here numbers of record is given to you, and in each block you have given the what is the numbers of record can accommodate. Now you can find the what is the numbers of block required for the main file.
10,000.
So
1 lakh divided by 10.
yeah, so
So 10,000 blocks, right?
so that is 10,000 block. Now one simple question: how many numbers of entry, therefore entry in the this block?
You'll have 10,000 entries in the index file.
If it is
Yes.
dense, if it is dense.
No, it
No,
is given in the
number of blocks is
numbers
10,000.
of
So one
blocks.
entry
Oh,
for each
Yeah.
block.
okay, okay.
So if you prefer the dense index, then those many numbers of entries in the
Index file.
index file, right?
Yeah.
So because every search key you have to put the one entry in the index file, right? Up to this is clear, right? What is the numbers of block?
Yeah.
Then you have to find the what is the block size, right? So block size is how you can find the block size.
Total size 100 MB divided by 10,000.
Yeah, exactly. So then you get the block size. So block size, if I converted that MB into KB, right? Then KB. So let's put on the KB. So that is equal to 1024 KB. So around you can say that is 10.24 KB, not KB. So this is the okay, just a minute. Block size. Okay, this is in KB. So you have to change that thing into means MB for better. Bytes also you can change into the bytes. That is also byte. Now you can calculate what is the value of that. So it's around. So in this way you can find the block size, right? My point is that. So you have to divide the total size of block. So if I'm not wrong, anyone can calculate, that is 1 into 1024 into 1024 divided by 10,000 bytes. What is the value of that?
I'm getting 0.20, 0.24, 0.2048 I'm getting.
10485, sir.
10
485.676.
10485.76,
0.76.
right? This is the bytes. So here it is given. So whatever the record are not spent are unspent and the fixed line. So you cannot. So you can say like this. This is the block size. This is one block, right? Hello. This is one block, and you can only able to. So these numbers of this is the block size. So we consider the lower value of that, right? So for our calculation, you can see this is the bytes we originally stored.
This is per block, right, sir?
Yeah, this is the block size.
Yeah.
This is the one block size. So you got the block size. What is the block size? Now you have to find what is the index file size. Then you can find the what is the numbers of block required to store the index, right?
So index file size is, I mean, the records are 1 lakh, sir.
Index file entry is your 10,000.
Yeah.
You already finds the numbers
Yeah.
of block. That
Yeah.
is the numbers of block equal to numbers of entries in the index file, in the sparse index, right?
Yes,
So
sir.
that is 10,000, and here it is given what is the structure of index file. You know that first one is the search key, and the second one is the pointer, that is pointed to that block, right? So search key, what is the size of each entry in the index file? So size of okay, size of one entry, that is 10 bytes. That is the pointer size plus 30 search key size, right? So that is the 40 bytes. You're getting getting this point, right? For one entry, this is the size, because one size occupied by the search key and the second one is occupied by pointer. So 10 bytes is occupied by this pointer, and the 30 bytes for this search key, right? So 40 bytes is for one entry. And tell me what is the entry for this numbers of size, index size.
10,000 multiplied by 40, those many bytes.
Yeah, so index file size is 10,000 into 40 bytes. Now you can find what is the block size is given. That is 10485 bytes. Now you can find what is the numbers of block required for index file, right? So you can simply divide that 10 1048. Can someone tell me that what is the value of that? So this is the byte and this is also
380, yeah, so 381.67. So we round it up to 382. Round up 882.
382. And now this is the
Not double excess, just 382.
380.
Maybe somebody else can calculate and keep me honest.
382.
So I think the math
I
I did
think
was
it is 38.
Okay, 38.82. Then you have to take the ceiling value of that, because this is a fraction. So numbers of block is not possible. So for our, so maybe one block is some half full, you can say.
right.
So that is 39 is your answer.
So we are taking 10,000 multiplied by 40, correct?
Yes.
And then when we divide it by 1048, we get 381 point something.
1085.
1085. Oh, not 48.
Yeah.
Okay, 85.
So that is
If
the
we do,
block size, right?
okay, so then I'm getting 368.66. So rounding it to 369.
69 or 39?
No, 369 I'm
1000.
getting.
Why did you divide it? We divided by 10485, right?
Yes.
Okay.
10485. Okay, I missed that. Okay. Yeah,
That's
then I'm getting
38.
38 point. Yeah, 38.15. So
38.
39. 39 is the answer. Correct, sir.
Okay.
Yeah,
So it
sorry for
is
that.
clear.
Yeah, it is clear. Yeah.
Okay. Now,
No, it's 38.14. So we always go up, or do we go down?
Up, right? Because
up.
you have to allocate at least 39 blocks, because if you
Correct.
allocate 38,
Yeah.
some of the
Got
data
it.
cannot be
39
stored.
blocks. Correct. Yep. True.
Okay, let me take the second question.
Sir, you always allocate the exact number of blocks, or you make some provision and round it up to nearest tens or something like that?
Okay, so when you trying to find the blocking factor, so blocking factor means how many numbers of record. So blocking factor means what I said. Blocking factor means the numbers of record you can accommodate in one block, right? Okay, exactly. So blocking factor, when you takes the blocking factor, right? So if size is, okay, let's give an example. Suppose this is 14 bytes. Let's take the block size is 14, right? This is block size is 14 bytes, and 3 is 3 byte. Just take example, this is the one entry size.
What is that? 3 bytes is what?
This is the record size.
Okay.
Record size in main file. Now, can you tell me what is the blocking factor? How many numbers of record you can accommodate in one block?
42.
No. So record size means what? One record takes 3 bytes, second records take 3 bytes.
Yeah.
Like this. So this is the total size of the block. So this is your whole block, and this is the record size. Then it will take, right, 14 divided by 3.
4 blocks. Sorry, 4 records maximum.
Maximum 4 record is possible. Why not it is 5? Because you cannot unspend. You can question it is given. You cannot broke one record, right? So maybe like this is record 1, record 2, record 3, record 4. But in the whenever come to the 5th block, you have not enough space to accommodate that.
Okay.
So you cannot break that record. So you have to move to the second record. So in that time, you have to take the lower value. Whenever you taking the blocking factor, then you have to take the lower value, right? Now, once the question is for what is the numbers of record that is required to accommodate for the index file, right? So why we takes the upper value? So here you can see 38.82. In that time we takes the upper value, right? So why is that? So that is because, so you can say that there is 38 block which are completely filled, right? But during the third block, 39th block, so it is a partially, that is the, simply you can say 80% is filled, right? Understand like this. So for that we count one extra block, that is a 39. Hello, I hope it is clear.
Yeah, makes sense. Yeah.
Okay, now move to this fourth question.
So that means it, so this is why they recommend that your block size should be an integer multiple of your record size, and ideally that the integer multiple should be also 2 to the power something, because then it will
Yes,
be right, because it will be
yes,
efficient for addressing as well,
yeah.
right?
So now fourth question is, consider the multi-level indexing with the 4 level as L1, L2, L3, L4, and the L1 is the innermost, and the L4 is the outermost. Let's the index blocking factor. Index blocking factor means how many numbers of record can accommodate in one block. So that is given the maximum 50, right? Blocking factor is given as the 50. Okay, with the information, answer the question 4 and 5. So question is, you have to numbers of blocks. In the L1 is the 1 lakh, and how many blocks are required for L2, L3, and L4. So you already know the concept of the multi-level indexing. So why we use the multi-level index? So multi-level index, here you can see, when for the data file you create a index, right? That index, so what is the use of index? So we can search the result in the database efficiently, right? But here you can see index file itself is so large, so that's for index file we required another index file. So that's why it is the we required the label 2 also. This is the label 1, this is label 2, this is level 3, and the level 4, right? So that we can do the search in the level 4, this is the outermost, and this is the concept of the multi-level index. In the level 4, the outermost, we store the entry in one block, right? So we go like this. So okay, let me explain this problem. So numbers of entries in L1 is given to you, that is 1 lakhs, right? So for another than the innermost, every other level in the multiple level are the sparse indexing. So sparse indexing means what is the numbers of block required for the L1, that is the numbers of entry for L2, right? Now if it is given to you the blocking factor is the 50, then what is the numbers of block required for the L1? So can you tell me what is the numbers of required for L1 numbers of block?
Oh,
So
100,000 divided by 50, right?
yes, exactly. So 1 lakhs, so
2000.
divided by 50, right?
2000.
So that is 2000. So 2000 is the numbers of entries in L2, right?
In
So
L2, is it?
yes.
Yeah. Yeah.
So you map, suppose this is numbers of block, right? Like this,
Oh,
right?
okay. So each block pointer, you're putting it into L2.
Yes, exactly. So that's why the numbers of entries in the L2 index is 2000.
Then we do another division by 50.
Yeah.
So it will
So
be
that
next level will be 40. L3
No,
will have
there are
40.
2000 entries. Now each
2000
block.
entries, right? So this is the numbers of entries. And now why I divided by 50? Because I requires the finds the numbers of block required for L2 also.
So now 2000 divided by 50 should be the number of entries going into L3.
Yes,
Yeah,
exactly. So that is 40.
40. Yeah.
So 40 is the numbers of entries. So here you can see your one block can accommodate 50 numbers of record, but you
So,
already have the 40 record,
so we can
right?
have one. We need only
So
one.
so we need only one block.
Yeah. In L4.
So that is high value. So that
No,
is one.
Why do you need L4 if 40 is there in L3?
So here you can see. So how you can search if there is a 40 numbers of entries in the L3. So how you can search that value? So you have to do the linear search in that block inside. Hello. If you want to retrieve the 32 record, means 32 means 31st record. If 31st record, if you want to retrieve, so you have to go in this block one by one, right? Hello.
I'm still trying to understand this.
So the search is linear within the level, but then is there a hashing, from there to there, or just a pointer from L4 to L3, L3 to L2? How does that? It's a pointer,
So
right?
this is the one search key and this is a pointer,
Okay,
right?
pointer. Okay,
So this is the general structure of the index file, right?
it's a pointer.
So
Yeah,
okay, let me finish this one. So L4 has the one blocks only, one
right.
entry, one
Yeah.
entry only, right? So
It has only one entry actually, not
yes,
one block.
yeah, one entry. So in this has only one entry. Suppose, and each entry is, suppose this is one, right? I assume this is one, and this is the 31st. 31st will come some year here, right? And in this block is come somewhere here, right? And here my block, okay. So this is a one entry, and this is the 31st entry, right? And this is a one entry, right? Only one block we store the first entry, first address of that entry. Now if I want to search that thing in the database, right? So how to go the searching happened, means I want to search 31, right? So I will first check L1 because L1 has only one entry, right?
You mean
So
L4, sir? L4.
L4, yeah.
Yeah.
L4 I want to search. So here you can see only one entry is there. So it will point it to this entry, right? Now I have to do the linear search here. So I have to access only one block here. Main point is that in the L3, I have to look only one block, right? Hello?
So basically, it will be that less than, greater than values, and based on that, you will
Yeah,
select the block where you have to refer to.
yeah. So in this way, you can see here I have to access only one block. This whole thing is accommodated in one block. Here also can see one block, and here also can see I have to access one block, right? And here also I have to select only one block, right? And since if data file is at some pointer is pointed to this data file, so this is the actual file, right? So I can do that also. So can you tell me in this how many numbers of block access is here to read actual record?
So can you ask the question? We didn't get it.
Okay, so no, if you have to see any data in the data file, so how many block you have to require to access to read the actual data?
In this case, only one block in the example you gave. Well, I guess
One,
four. Well, I guess four levels everywhere you are reading one block. The
exactly.
fourth, yeah, in the fourth one you are getting the final one. You have to go to the three pointers, and then finally the last pointer will give you the physical location in the hard drive where
Yeah,
the records are stored.
yeah, exactly. So first you have to look this block, then you look for this block, then you can look this block, then this block, and this original block. So here you can see numbers of level plus one. Hello.
Yeah.
So the original aim of the multi-level index, we means we reduce the numbers of entries up to till one block. right? So so that it will be easy for us.
So the real example will be, so there are instances where, see, the data set is, let's say you are working for Google and you have stored a Gmail of all people in the world. So you can imagine, right?
Okay.
This is our database. Each email is a record. So even if you have created index, if some user is going and searching, no way on the earth, even the index cannot be loaded to the memory, right?
Yes.
So then what you have to do is you have to break up the index and in this level so that your final block, that is L4, you can load to the memory. But even L3, L2, L1, you cannot load to the memory. So that means they are not in memory. They were either in somewhere else. Let's, some RAM drive or whatever, right? So
Yes,
this
yes.
is a good example where you have very, very, very large databases where the forget about the original data store, even the indexes are
Index
large
file.
enough to be loaded to the memory.
Yeah, yeah.
Then we
Exactly.
need multi-level index. There is no other way. Obviously, hopefully we don't have to deal with that. But if you end up working for a company which is like this Google or
Yeah.
whatever, then obviously this will be your bread and butter.
Okay. Is it clear now? Right. Hello.
Yes, sir.
Yeah.
Okay. Okay. I hope I will advise you to see the dynamic hashing. If you face any problems, then you can discuss on the next session also. If you face any problem, so please watch it.
So in your question, in the next question,
Okay.
I think you tried to answer that, right?
Yeah,
Multi-level
yeah, yeah,
access.
yeah.
Number
Multi-level
of
index.
blocks access is required
Numbers
to
of
read it.
block plus in one block that is required for the actual data you have to access. So that's why it is 5, right? So numbers of block means how many block, level of block means there is 4 level, right? L1, L2, L3 and L4, right? So you have to access every
Okay, so
block in each
four.
level and what is in the original database also you have to access.
Okay, so that is how it becomes 5 levels.
Yes, yes. Okay.
See, in that next question, in question number 6, I'm not getting that answer. If you look at it,
Okay.
there's a
Question number 6. Okay.
yeah, there's a
Every,
B tree based index of the order 19, and assuming each node of the B tree is 73% full,
okay.
and if the height of the tree is 3, what is the maximum number of keys that can be accommodated?
Okay, okay. Let me tell you what is the catch of this question is. So as we already mentioned in the previous session, we discussed about so what is the structured means what is the ideal case of so we already discussed about 2 3 4 tree, right? So what is the height of 2 3 4 tree minimum? What is the height of uh,
So
minimum?
minimum will be log of n with the base 4 or 3,
Yes,
3
yes.
actually.
So when will be that case? When 2 3 4 tree, every node has the 4 link is means
Available.
available.
Yeah.
Every node, right? Then it is the minimum height, right? And what is the maximum height? When every node
Everything
has the two
only
child,
two, only two. Yeah.
child. So here you can see, you can relate that question with this. So here it is given, assume each node of the B tree has the 73% full, right? So now you have to, so in this question you can do that like the similar to that. So you have to find, so
So what I did was, I mean, order is 19. So
okay,
basically log 19, log to the base 19, right? And the height is 3. So basically 3 times. So 19 into 19 into
no,
19
no, no,
and 73% of that.
No. So here you have to first assume the 73% of the node is full. So what that means? So if I take the 93%, so how many percent is full? So that is 93.73. So it will come around the 14, right? So now you have to assume it is in the question that given that each node is 73% full. So now you can assume that's the each tree as the this 14 order.
Order 14. Okay.
Yeah, you got the new P dash, that is the 14, right? So if now you know if P dash is your order, then what is the numbers of keys possible in each node?
P minus 1, P dash minus 1, 13.
Yeah. So that is the 13, right? So now you have to label 1. So that is label 0. Label 0 is your root node. Then label 2. Then label 3, right? Okay. So in label 0, you have only one node.
Yeah.
Numbers of node is 1. Then numbers of keys is possible 13, right? And numbers of pointer is possible 14, right?
Yeah.
On the second level, you can see second level, there is a 14 link for that, right?
Yeah.
So numbers of node in this level 1 is possible 14. Numbers of keys possible is 14 into 13. And the numbers of P dash is 14 into 14 for the next level, right?
Yeah.
Okay, similar to that. So numbers of possible in the level 1, that is the 14 into 14. And the numbers of keys possible 14 into 14 into 13, right? And so the numbers of P dash is possible 14 to the power 3, means you have to
14 cube.
Yeah. Now here you got the 14 into 14. So you have to one more time you have to do that. Here numbers of keys is in the level 3, that 14 into 14 into 3, 13. So you have to sum up this whole value. So you got 13, 14 into 13, 14 to the power 13.
Take 13 common, that will be easy.
Yeah, now you can do that 1 plus 14. So now it will be easy for you.
15, 196. Okay, yeah, this is.
14. So this will be only sum of, you can do that.
Yeah. The looks of it, it's 196 plus 15. It's about 200. 10 plus 14 cube is 1000 something. So yeah, it will be in that order. I think 38,000 looks to be the answer, the first option.
Yes, exactly. This is the answer, 38.
Yeah.
So there is a lot more difference between answer. You can eliminate in this way also. You have no need to calculate every time. So that is one advantage of the option.
Yeah, in the quiz, that's what we do, right? So when you're running out of time, you don't need to calculate. You kind of know the approximate, right?
Yes. Okay. I hope, that's it from today's session.
So I took it a little longer, but thank you very much for your patience. I really appreciate it. Yeah.
Thank you, everyone.
Yeah.
Thank you, sir.
Have a nice day. Bye.
Bye.
Thank you, sir. Thank you very much. Bye.